Hello, everybody. Welcome back. I'm Paul Brody. I'm the global blockchain leader for EY. I'm still the global blockchain leader. In fact, as I do every year in the summit, I always double check that I can log into my email and I haven't said anything profoundly wrong on the prior time. So I'm still here. I'm back. Today, actually, for the last day of the summit, I'm actually rocking a brand new shirt that I bought at Liberty's the other day. So I hope you like it. I did it for all of you. And today we have like a really awesome finale for our event, which is all about the underlying technology. If there's one thing that I'm really proud of, and we have really committed to, it's this idea that we should not just talk about, hey, public blockchains are great, but wouldn't it be nice if we had privacy? If we want to make that happen, we actually need to be involved in making it happen. And so the work that you're going to hear a lot about today in some fairly significant technical detail is stuff that we have really kind of rolled up our sleeves and dug into. And I'm really proud of the huge investments that EY has made, all of my fellow partners have made, in this technology, in developing privacy technology, and then in contributing it into the public domain. We have a terrific lineup of speakers and discussion today. And I'm going to start actually by handing it over to my colleague, Duncan. He is the head of research and development at EY and for blockchain. And Duncan, I'm going to let you tell people about the detailed agenda for today.
Great. Thanks, Paul. Well, this is definitely my favorite part of the ship, because today we're going to be down in the engine room of HMS Blockchain looking at the new ZK engines we've installed. Now, I think it's fair to say that if you've got a strategic roadmap for blockchain, and that strategic roadmap doesn't have the word ZKP in it, you really need to be worried, because this is a technology that's moving incredibly fast. But don't worry, we can fix that today for free. Just stay tuned and listen to all the talks, and you'll get a good view as to what it's all about. And just to develop the nautical theme, unless you've actually been on a long sea voyage, you'll have noticed there's been a bit of a sea change in the last year. We as crypto practitioners really can no longer ignore the effects of regulation and financial probity. We have to take those on board. We have to take them on board at a sort of organisational level, but actually there's something that technology can help us with as well. And so the second part of this session will be all about that. How can we use technology to make sure we're doing the sorts of things that the regulators are going to expect us to do, and in fact, good governance expects us to do. So that's an outline for today. If you are an EY employee, you'll all get questions that come up which you can answer. You can answer them for fun. If you work for EY, if you answer them, you'll get CPE credits. If you have any problems technically, there's a chat box you can type into. Somebody will help you out. If you get any questions during the day, then there's a Q&A button, and you can ask questions there, and I'll read them out at the end of the talk if there's time. And finally, and I'll probably say this again later, don't forget to collect your NFT for the day. There'll be a barcode that pops up at some point. So let's get on to our first speaker. Now, if you have done anything in blockchain, you will have heard of GM17, you'll have heard of Sonic, you'll have heard of Marlin. And one woman actually has been an author for all of those, and that's Mary Maller. Now, I think it's fair to say with her pedigree that she knows her times tables. But actually, what you may not know about Mary is she's a really good negotiator. And, well, many years ago now, I employed her to help me do some hard sums. And we had to negotiate the fees. And Mary started quite high, and I started quite low, as these things go. And we kind of came nearer and nearer and nearer. But then I got to the point where I couldn't go any higher. Mary wasn't prepared to go any lower. And so we were a bit stuck. And then I said, well, I'll tell you what, Mary, I can't go any higher, but I will give you free beer on a Tuesday if you come and work for us. And luckily enough, she said yes. And I think until today, she's the only person ever to have an EY contract with a beer clause in it. So, well, Mary, perhaps you'd like to come and tell us a little bit about ZKP.
Thank you for the introduction, Duncan. I should sort of say that I feel cheated because it was a WeWork and the beer was very much free for all employees, not just for me. So,
well, I didn't say I was terrible at negotiating. I'll leave you to it.
Okay. So today I'm going to be talking about what is zero knowledge to EY and the Ethereum Foundation. I'm going to start with a very sort of high level, what do I want from zero knowledge? What's my personal vision? I'm then going to talk sort of more realistic in terms of how is EY using zero knowledge. Then I'll talk about how does the Ethereum Foundation want to use zero knowledge. And finally, I'm going to sort of talk about something completely different, which is more sort of some research I've been looking at the moment. And that's a way that we can use zero knowledge over subverted RSA groups. I realize those are some technical terms there. Don't worry about it. This is just the outline. So I would say that one thing that is true today is that we very much have to trust that computations are done correctly. So when it comes to statistics, we have to trust that people have done statistics correctly, despite the fact they're quite easy to make up. We have to trust that any computations we're outsourcing to the cloud are being performed correctly by that cloud server that we've chosen. We need to trust that auditors are doing their job correctly, especially because auditors often need access to private business information, which really shouldn't be publicly available. Any kind of experiment, they can lie about their results. Bug bounties, this is actually quite a fun one. People have to reveal exploits to other hackers in order to be believed that there is a bug. But at the same time, in revealing that there is a bug, people can then exploit the bug. So there's a bit of a problem going on there. Mobile applications can be doing absolutely anything with their permissions. It's very hard to verify. And it's blockchain week. How can I not mention blockchain? If you want to have that your computations that you're doing on a blockchain are secure, you basically have to duplicate the effort. You have to make it so that everybody who is verifying this blockchain has to redo all of the work. So given all of this, I would say that we actually live in a very opaque world. One thing that could make this worse rather than better is that we are seeing some big advances in machine learning. And machine learning can be done to do great things, such as the images that I've generated for this presentation. They're all from DALL-E. But equally, we've got ChatGPT, which can be trying to make sure that it doesn't give you information about how to do illegal activity. But if you ask it in the correct way, then maybe it will give you information about how to do illegal activity. Also, these machine learning algorithms are also often using a lot of our private data, and we don't necessarily know that they're doing that in a good way. So what do we want to happen tomorrow? How do we want to change this? It would be nice. It would be nice if no organization could ever lie about any type of computation. And this could just completely change the way that we interact with technology. So maybe in the future, every computation you ever give will just be untrusted and ignored unless you give an accompanying proof that you've done the computation correctly. I'm afraid this probably won't solve world peace. But in terms of making the way that we interact with technology better, it could have some fairly significant consequences. Alternatively, it could just be the case that nothing changes and the technology doesn't take off in the way that we're hoping it to. We can't ignore this as a possibility. And I would say that actually when it comes to getting cryptography from the realms of research to the realms of real world, so to speak, this is something where maybe we don't have the best track record as a community because it's very difficult to do. So one case study that I have in mind is actually about pairing groups. Now, pairing groups are a tool which are used in zero knowledge all the time. They're really good for making very, very small proofs that don't use too much bandwidth over your communication channels. And the community has been advocating for a long time that pairing-based cryptography could be a good thing to have being widely used. One standardization body that is very prominent is the American one, NIST, and they started to discuss standardizing these curves back in 2008. After a long process of much conversation, much talks, they said it would be a good idea to standardize. But then nothing really happened. No standard has been produced for pairing-based groups to this day. Many companies will not use pairings for this reason, despite the fact that there has been 20 plus years of active academic and industry attention in this area. One even worse thing that could happen is, rather than nothing changes, but at least we have the potential to still make it happen, at least we could get there, is maybe zero knowledge gets outlawed. And a lot of you might already know about some of the controversy around zero knowledge, and so you might have an idea about where I'm going with this. So again, where I'm going is with a case study, and this is specifically about the Tornado Cash privacy-preserving system, which was being run on Ethereum. And it used zero knowledge as a key ingredient for how it was going to actually give people privacy for their payments. Now, zero knowledge can provide very strong privacy guarantees when used correctly. And what actually happened was the privacy guarantees were so strong that when some North Korean hackers managed to hack into some systems and steal some funds, they used Tornado Cash in order to transfer the stolen funds from cryptocurrency to actual fiat. Now, obviously, the US Treasury did not respond to this very well. They were not pleased about the fact that North Korea was getting funds through this mixer. And what actually happened was that not only did Tornado Cash get banned, but some of the key people behind it are still in jail, as far as I'm aware. It's all been quite a sort of scary process. And there's a very good episode about this, which I can recommend on ZK Podcast, if any of you want to sort of know some more information about that. So I've sort of said 3 alternative visions there. What I haven't said is I haven't said what zero knowledge is. It's a concept which was defined way back in the 80s. Obviously, it looked completely different then to how it looks now. But there are sort of 3 basic guarantees that you want to be able to ensure. You want it to be correct, namely that if you generate a zero knowledge proof, you can be sure that it's going to work. You want it to be sound in the sense that you cannot generate a proof for something which is not correct. And you want it to be zero knowledge in the sense that if you want to, you can hide any or all of the inputs to the computation in a way where you know that they are properly hidden. So my real takeaway from this part of the talk is to sort of say that if we want to get the most out of zero knowledge, we need to get the research, the implementations, the applications, and the politics correct today. So companies who are using zero knowledge for non-controversial applications today are incredibly useful for making that happen, especially the likes of EY, because we can show people, no, it's not just being used by criminals, this is how you do it properly. The EY, and not the EY, sorry, I say the EY a lot, I mean EY, and the Ethereum Foundation, that's the reason I'm getting it wrong, are both early adopters of zero knowledge, and I want to talk some more about that. So I would say that EY has been interested in ZKP technology since 2019. Paul and Duncan can correct you later if it was in fact earlier than that, but certainly I know they've been interested since 2019. One of the reasons is that they're very keen on having the transactions being run over public blockchains. And this is something that Paul Brody, the EY Global Blockchain Leader, talks about a lot. You heard from him before I came on. And he feels that public blockchains are the way forward, basically because companies will not easily reach consensus on which private blockchains to use. But public blockchains are, well, public. And sometimes there is information which you can't be broadcasting not only to governments and to auditors and sort of trusted third-party authorities, but also to absolutely anyone who wants to see that data, including potentially competitors. And And zero-knowledge proofs can basically stop that from happening. One person within EY who has been very actively looking at zero-knowledge is their head of global blockchain R&D, Duncan Westland. And he has been involved in releases for zero-knowledge proof blockchain transaction technology to the public domain to advance blockchain privacy standards. So what I'm running through here is some press releases regarding advances that EY have been making in terms of getting some of their key products from research into the public domain. So I can't quite read the date on there, but you'll sort of see them advancing chronologically. This one is saying that EY contributes a zero-knowledge proof layer 2 protocol into the public domain to help address increasing transaction costs on the Ethereum blockchain. One thing I should explain here, most of the work that EY has been doing on public blockchains has been on the Ethereum blockchain. And this is because Ethereum provides programmability in a way where it's very easy to be able to write smart contracts which can do interesting things. They have also collaborated with the Polygon protocol and have used its framework on scaling Ethereum solutions. On Ethereum scaling solutions. They've released their privacy-based protocol Nightfall, which I think you'll hear a lot about today. And they've also been contributing to a beta version of the zero-knowledge proof compiler Starlight, which is basically a tool that you can use to try and write zero-knowledge proofs in a way which is a bit more user-friendly. I mentioned 2 buzzwords there. I'll mention them again. One buzzword, Starlight. This is a user-friendly zero-knowledge proof compiler. Other buzzword, Nightfall. This is a privacy-preserving Ethereum transactions for business protocol. Ethereum has some fairly grand ambitions for zero-knowledge. What I have displayed here is the Ethereum roadmap for where we would like to go in the future and tasks that we're working on at the moment. You can sort of categorize them in 5 categories: the merge, the surge, the verge, the purge, the splurge. Where zero-knowledge proofs come in the long term is during the verge. And I've made the diagram a little bit smaller here because I've run out of space on the slide. So the idea behind the verge is that it's not just about having Verkle trees, it's about making verification fast. So the idea here is that the entire of the Ethereum blockchain would be under a zero-knowledge proof. And this zero-knowledge proof would be a very succinct one, which is very quick to verify. So this would basically make running a full node something that goes from being something that you need a lot of infrastructure and a lot of capability to be able to run to something which you could run a lot more easily. And that would also mean that we could run more advanced applications on the blockchain without it causing a huge scalability issue. So all of this is about scaling. Currently, every Ethereum transaction has to be recomputed by every single validator, which severely throttles the total throughput. I say zero-knowledge proofs can solve this. Actually, they don't even need to be zero-knowledge for this. It would be enough for them to be succinct proofs. But zero-knowledge has the additional benefit that if you want to hide some information, then you can. One team within the Ethereum Foundation which has been actively working on this more than any other team, I would say, is the privacy and scalability team. So I'm making space there. So when we say that we want to be able to have transactions inside a zero-knowledge proof, what we really mean to say is that we want a zero-knowledge roll-up. We think that zero-knowledge rollups might be fast enough with Nova implemented over a magic group, or Fry, or the breakdown polynomial commitment scheme, or all neatly hidden inside a KZG proof. And these are sort of some strategies which we're being seen by quite a few companies at the moment. There is Scroll, there is ZK Sync, there is Starknut, there is Polygon Hermes. There's probably more that I've forgotten. I'm very sorry if I have missed your pet project off this list. One thing that all of these share in common is they're all currently looking to be a layer 2 application. And what that means is rather than being on the base chain for Ethereum, they're going to be written on a smart contract and done on top of Ethereum, but that you would still be having to go through Scroll or go through ZK-Sync or go through Starknet. Starknet is its own thing, I should say, its own blockchain, in order to get that scalability. If we're talking about not so much layer 2 applications, but layer 1 applications, I would say that there are some complications. So as you all know, that zero-knowledge proofs can provide really strong privacy guarantees when they're used well. The privacy guarantees are so strong that you might not actually know when your system is under attack. And this is something which our security research team is very aware of and worried about. And one thing that they have sort of said, to me at least, is that they don't think ZK can be used on the base layer because you lose transparency over the total supply. So on the Ethereum base layer, we cannot depreciate old code as well, which is another sort of thing we have to address here. So any new library introduced must be maintained for the rest of time, whatever time means. An extra thing is that it's quite rare for developers to have the expertise to maintain super specialized cryptography libraries. So we've kind of got two things going on here causing us worries. On the one hand, if our zero-knowledge protocol is being attacked, we might not know it. And on the other hand, the people who are maintaining our libraries really don't want to do this. So if we want to be able to tackle some of these issues, I would say that we need standard efforts. One standard effort, which I'm very actively involved in, is the ZK-proof standardization effort. And this is a global movement to standardize and mainstream advanced cryptography by building a community-driven trust ecosystem. And hopefully this should help with certainly concerns about how do we implement them securely, because we know that we're not just taking some hot off the press research that came out yesterday. We're taking a protocol which has been reviewed, which has been audited, which has had many people in the community look at, which has lots of incentive for people to look at, because breaking a protocol which is being standardized gets you much more fame and glory than breaking any old protocol would. And hopefully this should give us some sort of stronger guarantees. Currently, the working groups are trying to formally document at least one general purpose proving system. It would be nice to have multiple, but if we can get at least one properly documented, we would consider that to be quite a good feat. We're working very closely with NIST, as well as other experts from academia and industry. And I would say this is a very difficult task, but the payoff, if we get it right, could be real. Okay, enough of this. I'm now going to change track completely. I'm a researcher. Have I done any research recently? Yes, I have. So zero-knowledge proofs are typically based on assumptions. These assumptions are something which we assume are true, and if they are true, we know that our proof is good. If they are not true, then our proof is probably bad, but we have lots of reason to believe that the assumptions in question are good. So an example of what you might say here is you might say, my protocol is secure if and only if the discrete logarithm problem is hard. And this is something which many of your favorite schemes are based on, certainly including Grot16, GM17, bulletproofs. Each underlying assumption introduces many different trade-offs. So if we're talking pairings, they're very short. Discrete logarithm, no trusted setup, LWE are post-quantum secure. One assumption type which I've been looking at recently is unknown order groups. And these are really in the kind of trade-off space, I would say. They're mediocre at everything. They've got medium proof size, medium prover time, medium verifier time. And they can be constructed using two different types of groups, class groups and RSA parameters. Class groups, I would say, are a very good idea, but for some reason, this just hasn't really gained traction yet. RSA groups have a very difficult trusted setup. So many of you might have heard about the sort of GROT16 setup that Zcash have been running a few years ago, and they're like, okay, that's difficult, but there's a way to do it. The RSA one is much, much harder. So the question that we were asking is, can we just use bad RSA parameters? Can we just choose our RSA parameters in a way where they might be insecure, but we can still build a proving system out of them? Largely, I'd say the answer to this is yes, but there are some caveats. Firstly, it's designed in the designated verifier model, which means that it's not publicly verifiable and only one verifier is able to actually check that the proof is correct. And the other is that we have some fairly expensive pre-processing. So before you generate any proofs, you have to do this sort of one-time computation, which is going to be pretty expensive. But it does contain a really fun trick, basically to make the protocol non-interactive. So rather than I talk to you, you talk to me, I talk to you, you talk to me, I talk to you, okay, we now agree that this thing is correct. Instead, I just send you one proof, and you can check that that is correct directly. So in short, we have 128 encrypted verifier challenges, which are combined in a random way in order to get one random verifier challenge, and that's the kind of trick that allows us to do this. So in terms of conclusions, what is my personal vision for zero knowledge? Well, I want zero knowledge proofs to guarantee the correctness of all important computations without risking any privacy implications. How is EY using zero knowledge? EY has released a technology for user-friendly, privacy-preserving transactions over blockchains. How does the Ethereum Foundation want to use zero knowledge? We want fully snarked base layer as part of the Verge. And can we have zero knowledge over subverted RSA groups? Kinda. It's tricky, but it was fun to work on. Thank you very much. Are there any questions?
Thanks, Mary. That was marvellous. I think two things stood out for me there. One is the use of snarks in the Ethereum layer one. That would be game-changing, wouldn't it?
Yes, we know it's ambitious.
Suddenly you can sync on your mobile phone, though. That would be awesome. So I really hope you manage that one day.
Future goal, future goal.
And I think the other thing for me was to really appreciate some of the novel security aspects that you get with ZK snarks. And this is the trouble with mathematicians. When they say zero knowledge, they actually mean it, don't they?
They do, they do.
And so, you know, finding you don't actually know if you're being attacked and how you deal with that.
Yep, you very much have to bear it in mind when you're designing a system.
Yes. So I don't know if we have any questions. No, we've no questions for you.
That's okay.
So it sounds like you explained everything to everyone perfectly.
Awesome. Oh, thank you very much.
Well, thank you very much, and we'll see you soon.
See you soon. Thank you.
So our next talk is from a guy who I've known for probably just over a year, Roger Tolle. He worked with me on Nightfall for a while. He strikes me as a superb mathematician, but an incredible coder. I mean, how that guy can turn deep mathematics into lines of code as fast as he does, I have no idea. I really wish I could do it. It's awesome to watch. If you ever get a chance, just go along and just watch him code. It's fantastic. He's like ChatGPT, but he can do he can do zero knowledge as well, which, by the way, ChatGPT can't, where our jobs are safe for the moment. Now, what we're going to hear about today is, to my mind, a very exciting development, because when Roger stopped working on Nightfall, he went to work with Jordi Bellina on Polygon ZK-EVM. Now, a lot of you may know this is a scaling roll-up that has just been released by Polygon. It's fantastic. If I had an optimistic roll-up, I would start to be worried by this technology. I really would. So, Roger, perhaps you can tell us a little bit about it.
Yeah, can you hear me?
We can, yes.
Nice. So thank you for those very kind words about me. I don't know if I'm that good, but
I'm sure you are.
so I'm here today because I'm very honored to be here, and I'm gonna talk about Polygon ZK-EVM. And the way this talk is gonna work, I'm gonna try to give first a bit of motivation why ZK-EVM is not only Polygon, because as Mari has just said, there's plenty of different solutions. But why ZK-EVMs are needed? Then I'm gonna jump into what's Polygon ZK-EVM, and I'm gonna do my best to explain how Polygon ZK works in an easy and understandable way. And finally, I will do a quick demo. So I will show you how you can interact with Polygon ZK-EVM. So the first thing I want you to think about is why. Yeah, sorry, the slides moved. So the first thing I want you to think about is Ethereum. What comes to your mind when you think about Ethereum? You may think that it's a very used network, probably the most used network in blockchain right now. You can also think that it's very mature. It's been running since 2014, but also it can come to your mind that there's some downsides, right? It's not fast and probably not cheap neither. And when in times in which there's a lot of traffic, this gets considerably worse. And probably if you've been on the blockchain space for a while, you've noticed that. And this, in fact, is not a problem only of Ethereum, but it's what's called the decentralization trilemma, that states that there's currently no system that is secure, decentralized, and scalable at the same time. But we want to have mass adoption for blockchain, right? So we need to find a solution on how to scale it. There's no other solution. And in Polygon, we believe that Ethereum is the perfect blockchain, but we needed to find a solution on how to scale it. And in order to do that, I like to think blockchain as 4 different layers. There's a consensus layer, which is basically the one in charge of ordering transactions, data availability layer, which is in charge of storing the state, settlement layer that regards finalization, and the one we're going to focus is the execution layer. That is the one that executes the smart contract and processes all the transactions. So rollups and rollup scalability focuses precisely on that execution layer. And the main idea here is that what any rollup tries to do is offload those computations from the main network, in this case Ethereum, to a separate layer. So what does it mean exactly to process a transaction? So each blockchain, Ethereum, but also the separate layer will have an state, right? So you can think of the state of all the information that's stored. For example, you can think of in Ethereum, there's many accounts with different balances, and all this state is then hashed together in a value that's called state root. And I mentioned this because this concept will appear a lot during this talk. So basically, what happens is when Ethereum executes a smart contract, it processes a transaction that modifies the state, and they modify this state rule. So the idea of rollups is that we're going to take away all this computation, and not only we're going to, instead of processing transactions one by one, what we're going to do is we're going to generate batches, which a batch is basically a group of transactions processed together. And then we're going to send those batches to L1. And here there's 2 different approaches. You could say that, okay, I'm done. Not really that simple, but optimistic rollups, you basically allow anybody to check the computations you've just done, and if you're wrong, they will tell you. Or you can use zero-knowledge technology to generate a proof that the computation that you've done is actually correct, because doing all this computation is quite expensive. So what zero-knowledge technology, which has been a hot topic for the last years, allows is that you can generate a proof that the computation has been done properly, and then you can post that proof and verify in a very easy way that that computation was correct. And that's a rollup, right? But you can have many flavors. You can have a simple, nothing simple, but you can have a payments rollup, or you can go big and try to build a ZK-EVM. So what's a ZK-EVM? Oops. So ZK-EVMs are virtual machines that execute smart contracts in a way that is compatible with the existing Ethereum infrastructure and also with zero knowledge. So that means it's a rollup because we are doing all the computation, but of everything the Ethereum is computing. And also important here is that the ZK part starts with zero knowledge, because ZK-EVMs not only does all the computation, but then they will generate a proof that the computation is done properly. Here, there's different approaches in order to develop a ZK-EVM, and there's a classification that Vitalik did a few years ago when ZK-EVMs exploded. But mainly, I would say there's two big types. You can be either compatible if you built a specific compiler that compiles the smart contracts in a format that's optimal for ZK, or you can be equivalent if basically your smart contracts are in this ZK-EVM are processed in the same way as in Ethereum. And why do we need ZK-EVMs? What are the main goals? Because why are we building this? So the reason is because we want to reduce the fees, and we want to also increase the transaction throughput. So now we know what's a rollup. Now we know what's a ZK-EVM, but what's really Polygon ZK-EVM? So Polygon ZK-EVM is an equivalent virtual machine that's designed and developed to emulate the Ethereum virtual machine. And what's the Ethereum virtual machine? Basically, every time Ethereum is the part of Ethereum in charge of processing transactions. And what Ethereum does when processes the transactions or the smart contract executions is that it breaks down that execution into very small instructions, which are called opcodes, and executes them. So what Polygon ZK-EVM does is we recreate all these opcodes, but in a zero-knowledge friendly way. Here in Polygon ZK-EVM, we use, as I said, there's two parts. The first one is doing all the computation, but then we also need to generate a proof of that computation. So that's why we use zero knowledge in Polygon ZK-EVM. We say that we use zero knowledge as validity proofs. And here we'll see later that there's different types of zero knowledge proofs. The most important ones are FNARKs and STARKs. And we'll see later that we are using both in our system. Also, there's in Polygon ZK-EVM, we are very focused on security. And the fact that we've decided to go for an EVM equivalence approach makes that we are inheriting all the security from Ethereum. So that's very important for us. And in fact, Ethereum runs what's called the Ethereum test vectors that checks that all functions are, all the executions of the Ethereum machine works properly. So we are running all these very same tests in our system to make sure that everything works as expected. And finally, another important feature that of Polygon ZK-EVM is that since we use validity proofs, withdrawal is very fast compared to other solutions. In our case, from the user perspective, you will be able to withdraw as soon as a validity proof is posted, as we will later see. I just jump. Okay, so now I'm gonna try to jump into how is Polygon ZK-EVM built and how it works. Just a few things before starting. I want you to know that Polygon ZK-EVM is a very complex solution. So I'm just gonna give you an overview and present the main parts, the main components. And also that there's some terminology. I'm gonna use L1 and Ethereum indistinctively, and I'm gonna use L2 and Polygon ZK-EVM also indistinctively. And also when I refer to on-chain, I mean posting to Ethereum. So, and this slide is probably not specifically from Polygon ZK-EVM, but okay, so now we know that we want to build a ZK-EVM so that we can scale Ethereum. What do we need? So we are building a separate layer, right? At the end, ZK-EVM is a rollup, and a rollup is a separate layer that handles the execution. So the first thing we need is some tool, in this case a bridge, that allows us to interact between Ethereum and Polygon ZK-EVM. In our case, we have a very special bridge that I will talk more about later that has a very special feature, and is that it's trustless, which means that we don't require any third party to do this transfer of funds. And so then we have the bridge, which allows us to transfer funds from L1 to L2, but now we also need to interact with L2, right? So then we have the ZK node, which is a regular node that allows us to interact with Polygon ZK-EVM and is Ethereum compatible. And finally, we have the prover, which will be in charge of generating those proofs I was mentioning before. So let's say I'm a user and I send a transaction to L2 using the node. So now what happens next? What happens inside Polygon ZK-EVM? So the transaction is posted on L2 with fast finality. The sequence, because the sequencer gets the transaction and processes it, and gets what we call the trusted state. What's the trusted state? Basically, is the state, given the current state and your transaction, the state that is that results from that execution. But it's trusted because at this point of the flow, you need to rely on the sequencer. The sequencer is broadcasting this state, so you need to rely on them. Then what the sequencer does is the first service that I'm going to talk about. It processes the transactions and it puts them together and generates batches, right? Because at the beginning of the talk, when I was talking about rollups, I said that rollup basically is batches of transactions. So the sequencer is the actor in charge of doing those batches and sending it to the blockchain, in this case Ethereum, using this sequence batch function. And when this happens, we say that the state that we call trusted state is now a virtual state. And what does this mean? Because when I explained trusted state, I said that that you were relying on the sequencer. Now you don't need to rely on the sequencer anymore, but you can get the batch of with all the L2 transactions directly from the blockchain. So then L2 nodes can synchronize in a trustless way. But we're not done, right? We've generated some batches and we've posted those batches on chain. But now we're missing the proof. We need to somehow generate a proof that all the computation that has been done is properly done. So for that, we have the aggregator, which basically picks the batches from Ethereum and sends it to the prover, which will generate the proof of that computation and will send it back to Ethereum. At this point, we say that the state is verified because there's a proof verifying that state, and that that state achieves finality. At this point is when users will be able to withdraw, because the withdraw transaction has been put into a batch, and that batch has been proved. I jumped. Okay. So I said that the sequencer generates the batch, right? In fact, I should have said trusted sequencer, because right now there's a centralized sequencer, the one that is in charge of receiving these L2 transactions, order them and put them in a batches. And what the sequencer does, basically given the current state root of the blockchain and all the transactions that are getting into that batch, it runs a deterministic program that we'll see in a second how this works, and it generates a new state word. But what's really happening here? What's this deterministic program? The intuition here is that you can think of Polygon ZK-EVM as a processor, as a tailor-made processor designed to execute the smart contract and process transactions in a zero-knowledge friendly way. So as any processor, there's the storage, which allows us to store the state, there's a RAM, and there's the ROM, which is the most important component. That what the ROM does is it interprets all the EVM opcodes and generates this new state. To do this process, we've developed 2 new programming languages. One of them is called PIL, which stands for Polynomial Identity Language, and the other one is ZK-ASM, which stands for ZK Assembly. And we've also built several subprocessors or state machines that allows us to perform these computations in an optimal way. For example, we have a binary state machine, which allows us to do the binary operations. We have the arithmetic state machine, which allows us to perform additions, subtractions, multiplications. Or we also have the hashing state machine, which allows us to perform K-checks, Poseidon, SHAST. So what we have so far is that the sequencer generates batches and sends it to the blockchain. But we're missing one part. We're missing that proof that we were mentioning, that validity proof. So the naive approach here would be, okay, so we have we have some batches, so we'll generate a proof for each batch, and we'll send that proof to the blockchain. That would be the most naive approach, but that's not very efficient. So we go one step further, and what we do here is what we call the infinite recursion, which basically means that we generate proofs that verifies another proof. And what happens here is that we first generate a proof for each batch, and then we aggregate those proofs together by generating a proof that verifies those proofs. And at the end, if you think like this about tree, we will end up having a single proof that verifies all the batches. This is done thanks to Starks, which is one type of zero knowledge proof that allows us to scale very well. But they have a major problem, and is that Starks do not perform really well on chain. Because at the end, what's the goal of all this? We want to generate a proof that will be verified on chain. So now we have a proof that verifies all the batches, but we want to verify it on chain. So what we do is as I said before, that we're using both Starks and Snarks. So we verify that final proof with a Snark, and we send that proof, because Snarks are much more cheaper on chain, and we send that proof to Ethereum. And in Ethereum, we have a smart contract that verifies that proof. Once that proof is sent, we say that, as I said before, that the state is verified and we achieve finality. So here's some statistics about Polygon ZK-EVM. For example, I was saying that the cost of verifying a proof is much cheaper thanks to using Snarks. In our case, verifying this final proof costs us around 360,000 gas, which as of today, if I'm not wrong, is around $10 to $20. Also, we're generating this final proof once every hour. And for example, as per reference, each batch can handle up to 500 ERC20 transfer transactions. So then if you think about what's happening is that maybe you are proving n batches. Imagine that we're proving at once 20 batches. If you multiply that by 500, we're proving thousands of transactions with a simple proof. And here also on the screen, you can see some other information regarding the recursion and how long does it take to generate the proof, to do each step. For example, you can see here that generating the batch is the most time consuming, which makes sense because remember that to generate a batch, you need to do all the execution that Ethereum would do in zero knowledge way for thousands of transactions. And so what we've seen so far is that user uses the bridge to move some funds to Polygon ZK-EVM, and then the user sends a transaction to the network. The sequencer grabs that transaction and generates a batch. The sequencer sends that batch to Ethereum, and then the aggregator picks those batches, sends it to the prover, and the prover generates a valid proof. That's what's happening high level inside Polygon ZK-EVM. But what's really cool is that from the developer perspective, there's no difference between developing in Ethereum or in Polygon ZK-EVM. Since we are EVM equivalent, in addition to also inheriting the security, we allow developers to keep using the same tooling. They can keep using Hardhat, they can keep using Truffle, Remix. There's no need to learn a different programming language. They can keep using Solidity and Yule, also known as assembly. The gas model is the same. So basically, we could say that it's almost a frictionless system, right? So if you know how to deploy a smart contract in Ethereum, you will be able to do that in Polygon ZK-EVM. Also, and one thing here, and why, okay, so why you should use a Polygon ZK-EVM, right? Because it's not only frictionless, but it's much cheaper. So right now, I think it's around 5 to 10 times cheaper to do a transaction in Polygon ZK-EVM rather than Ethereum. So now I'm going to share my screen and I'm going to do a demo, which will consist on 3 parts. The first one, I will show you the bridge. I will perform a deposit, and I will talk a bit more about what I said about trustless bridge. Then I'm going to connect to Remix and deploy a very simple smart contract just to show that it's exactly the same contract that you would deploy in Ethereum. And finally, we will explore Etherscan a bit so that I can show you everything that I've explained to you so far. So, and now let's hope everything goes well. I'm going to share my desktop on my screen. Can you see it now? I hope so. So here we have Polygon ZK-EVM bridge. Of course, I'm in testnet. I'm gonna do all this in a testnet environment. But here you can see the bridge, and what the first thing we're gonna do is we're gonna go here, and we're gonna send some ETH from Gurley. Let's say 0.02, and let's bridge it. Now MetaMask asked for confirmation. I have to switch network because I was connected to ZK-EVM testnet. That's fine. And now it should tell me to sign. Yeah, here it is. So let's wait till MetaMask. Okay, so now it is. And now we're going to confirm. And now we need to wait for the transaction to go in. Remember that this is the very first step. So we are connecting to, we're sending funds from L1, in this case, Gurley, because it's testnet, to L2. And it's a transaction successful. And one very interesting thing here is when we go to transactions, it says, okay, you see a loading here, waiting for funds to arrive. The estimated time is 15 minutes. Why is that? Because remember what I said about the bridge? I said that the bridge was trustless. And the way we achieve that is on Polygon ZK-EVM chain, in addition to the state, we have another value, which is the global exit route, which basically is the hash of all the deposits and withdrawals made from one chain to the other. And the thing is that this state is updated every time a batch is sequenced. So what's happening here is that now L2, the sequencer is aware that there's this deposit. And when the sequencer generates the new batch, we'll update the hash of all these deposits and withdrawals, so we'll be able to claim. Since this may take a while, I'm not going to wait for that. And as you've probably seen before, I already have some funds. Of course, that's not a real $1,000. It's just fake money. So we're going to go to Remix. This is a very simple smart contract. In fact, if you've ever used Remix, is the template they give to you, and it's just a very simple contract that stores a number. So the first thing we're going to do is we're going to change network, because right now you see that I'm connected to Girly. So we're going to go to MetaMask. I'm going to change the network. And then I'm going to deploy. Okay, so now invalid transaction. Thanks a lot. So let's connect again. Now, great. So now we're deploying. You see that the fee is ridiculously low. It's 0.0000 ETH. And we'll confirm. And if everything goes fine, yeah, the transaction went in. There's a very fast penalty here. If you don't see the pop-up of MetaMask on top of my screen, because I am using multiple tabs and it appeared on the other one. So now we're gonna store a simple value. Let's just pick a random number, I don't know, like 33. We'll store, again, it will ask MetaMask for confirmation. So and now again, you can see the fees 0.000002 ETH, which is very, very, very low. And as I said, in mainnet, using ZK-EVM has a benefit of paying 5 to 10 times cheaper fees. And we'll confirm. And again, you see the transaction went in, so we can retrieve and see that the number was updated. So this was the same you would do in Ethereum. And now what we can do is we can explore a bit what's going on an Explorer, right? So let's gonna copy the transaction hash. I'm gonna go to Polygon ZK-EVM testnet Etherscan. And the first thing you can see here is that there's two things showing up in this tab. There's the latest transactions, in which you can see all the transactions that has been happening. And there's the latest confirmed batches, which means the batches that are sequenced and sent to the blockchain. So we're gonna first search for our transaction. And you can see here that it's regular Etherscan. It shows the block. In this case, it's the Polygon ZK-EVM, the L2 block in which this transaction is included. And it says confirmed by the sequencer. What does this mean? It means that the sequencer has processed this transaction, but it's not already in a batch in L1. And also, if it's not in a batch in L1, it's not verified. So since this process takes a while, what I'm going to do is I've been doing some tests, and we can go through my transactions, all transactions, and I can pick a random deposit. Let's say this one that I did 2 hours ago. And if we get inside, you can see that there's more details in it, right? So there's the block. Now, instead of confirmed by the sequencer, it says there's a number of L2-1 block confirmations, but also there's this part of information here, and which basically there's 3 main things here. There's the transaction batch index, which is the batch in which this L2 transaction was included. Then you can see the sequence hash, which is the transaction hash in which the sequencer sent the batch on L1 Ethereum. And you can also see the transaction hash in which this batch containing your transaction was verified. So here's the full process with I've explained to you. First, the user sends a transaction to L2, the sequencer puts that transaction on a batch. That batch is sent to L1, and then finally the prover generates a proof for that batch. And for example, here, if we get inside the batch index, we'll see some additional information. For example, we can see that this batch contained 22 transactions, or we can also see the state root that, as I explained in the beginning of this talk, we can also see the sequence and verify batch transaction hash. And also we can see the global exit route, which is what I explained about the bridge, that it is the hash of all the deposits and withdrawals, meaning all the movement, all the funds movement between chains. And you can also see the batch number. And if we get inside, now you can see that we're in Polygon Scan because it's the explorer for the L2 blockchain. If we get inside, for example, the sequence transaction hash, you can see that it redirects me to Girly, because now we are posting that batch into L1. And what I want to show you here is I'm going to check the account to which this transaction was sent. And you can see here the 2 methods I've been explaining. on one side you have the sequence batches, and on the other hand you have the verified batches. Here you can see that, for example, on testnet, a batch is sequenced roughly every 11 minutes, I would say, and the verified batches happens once every half an hour. And so the last thing I want to mention here, I'm gonna get back to the wallet. And if you're really interested in Polygon ZK-EVM, I strongly recommend you to go to the ZK-EVM wiki, which is it's opening here, which it's a very extensive documentation, not only of what I explained, but all the components that make ZK-EVM, how is it built, and it's a much more detailed explanation of what I've just tried to summarize here in 30 minutes. And so I think that's all. I hope you learned a bit of how ZK-EVM works, Polygon ZK-EVM works, and if you have any questions, feel free to ask. And thanks a lot. I think that's it from my side.
Well, Roger,
okay, so yeah.
Roger, thank you so much. That was completely brilliant. I'm in awe of what you guys have achieved. 18 months ago, I saw people working on this, and I thought, that's 4 or 5 years away. That's properly difficult. And yet here you are. Marvelous.
Yeah. And the thing is that we're just starting, right? So now we have, we went live on March 27th, but now we need to really scale, because now it's way cheaper, but we need to do several optimizations that it actually scales Ethereum. So I would say that the journey is just starting rather than finishing.
Indeed. This is the thing with ZKP. If you don't keep an eye on it, it will come and bite you. It really will. So,
yeah.
So we're a little tight for time. So we'll pass on the questions. But Roger, thank you so much. We really appreciated that.
Thanks a lot for inviting me.
Okay. Well, I'll move us on to the next talk. So this is a little closer to home. We have 2 of my best R&D engineers, and they're going to talk about Starfall. Now, I think Roger showed very well what you can do when you use ZKPs for scaling. It's interesting to speculate, what can you do if you actually bring in privacy as well? And the answer is, well, you can do this. So over to Elias and Miranda.
Thank you, Duncan. Yeah, so there's been a lot of talk about privacy this summit. Paul opened his keynote mentioning essentially 3 of the main tools that we use here in R&D at EY. So we'll cover a couple of them at the start before we introduce Starfall. They kind of form the basis for how the Starfall product itself is developed. We do have a demo, but we'll go through the future plans as well and then save the demo for the end. So what are the privacy tools that we use here at EY? Essentially, it's 2 of the original technologies that we developed mostly to scale private computations on public blockchains. The first being Nightfall. Nightfall being designed for efficient private transfers. It is a layer 2, which means that we get fast, low-cost private transfers at a fraction of the cost of what it would be on the base layer. The base layer here being any EVM-compatible blockchain, so think Ethereum or Polygon. We have some additional features in Nightfall, so the ability to privately mint and burn tokens. This is really useful for enterprise that want to tokenize their supply chain or their value chain, whereby doing so publicly would reveal sort of second-order information like production schedules. Finally, we have a larger anonymity set. So given a generic rail, so Nightfall can be used for payments rails or for just transfers in general, we're able to maximize the anonymity because large-scale enterprise transfers are mixed in with just regular people trying to perform private transfers. For Starlight, I will hand over to Miranda.
Yep, I can introduce Starlight. So I think as Paul mentioned on Tuesday, Starlight is actually a compiler. What it outputs is a privacy-preserving zero-knowledge application based on a cryptographic commitment system. It maintains the original logic that was input in the form of Solidity code, and it proves that that code was executed correctly rather than doing it in the open. For that reason, we say it's designed for domain experts, so those who know how to write Solidity and smart contracts, as these are the inputs to the compiler, and then the output is a full zero-knowledge application that maintains privacy.
Cool. So just a little bit deeper into Nightfall. So as I said before, it's a ZK optimistic rollup, specifically designed for private transfers. As a layer 2, it means we inherit the security and consensus mechanisms from layer 1, which is great. Just going over the overall Nightfall network and some of the participants, we start off at 1, which is right at the bottom, with the transactors. So transactors are essentially users that want to utilize private transfers on Nightfall. They will build transactions that contain zero-knowledge proofs locally and send them up to layer 2 block proposers, or sometimes they're called sequences. The role of these sequences are essentially to collect these transactions and roll them up into layer 2 blocks that are then submitted onto the base layer. These layer 2 blocks actually take the form of transactions in the base layer. So eventually, miners or validators in these layers will then include them in those standard layer 1 blocks. When that happens, on-chain contracts update their state to track the overall Nightfall 2 state, or Nightfall 3 state, I guess, the layer 2 state. And we do that so that we guarantee that there's a degree of on-chain data availability. This is really good because what it means is that new users, auditors, or external parties that want to verify the layer 2 state can do so directly using purely the on-chain, the layer 1 on-chain state. So they don't need to trust anybody to provide that state to them. Additionally, this is really important in an optimistic world because we have the concept of challenges. These people monitor the layer 2 state through the layer 1 and submit forward proofs if they find invalid transactions or blocks. So that's Nightfall.
Yep, so I can introduce Starlight. So here, as we said, Starlight is a compiler, but more technically a transpiler. So it takes in already written code and creates a full application from it. We can see the input smart contract represented in step 1. So that is smart contract, but any code that involves a state or variable that you want to keep private. For example, here, if you had a function that raises a purchase order and you wanted all purchase orders to be private, then that would be represented by the line in red. So all logic involving that would be compiled into a zero-knowledge circuit, which not only copies over the logic that is being done, but also converts any states into a commitment, where whenever we change that state, we prove that that computation has been done correctly and emit a new commitment representing that state, nullifying the old one as well. So the whole application generated by Starlight also includes the layer 1 verifier contract, where you verify the proofs, or the orchestration code that allows you to set up the circuits, generate the proofs, and verify them as well, along with a commitment tree, so an accumulator that keeps these commitments and you can prove membership of them, and of course APIs as well, so you can call the functions. Yep.
Right, so on one hand, we have Starlight for general purpose private business logic. And on the other hand, we have Nightfall, which does generic private scalable transfers. The idea behind Starfall is to combine the two so that we get a layer that can do scalable private general, or general private, I should say, business logic. So what is Starfall in a sentence? It's essentially the ability to take fast, low-cost private transfers that occur in large anonymity sets, and then use them as inputs to private computations within business-specific zero-knowledge applications.
Yep, so here's an example of how Starfall would work. So you see in the middle, we have the Nightfall layer 1 contracts and the Starlight verifier contract as well. The only requirement really being is that they are both deployed on the same EVM-compatible blockchain. You can choose between pretty much any EVM-compatible blockchain, but as long as they're deployed on the same one, everything will work. So here, one example of using Starfall is that in the Starlight-generated zero-knowledge application, you have some code that you want to execute only if you receive a valid proof of payment. Valid being whatever you choose valid to mean, some code execution on that. So you would do a private transfer within Nightfall from party A to party B. And when that transaction is rolled up into a block, the transaction hash and the block hash will be kept in the Nightfall layer 1 contracts. Again, completely under privacy, so nobody knows exactly what is inside those commitments, apart from those who have the private key. And then in Starlight, we will use that transaction hash as an input to the zero-knowledge circuit and create a proof that goes on chain. And that proof will only be verified if, of course, the proof is valid, but also if this transaction and block actually exist and are valid anyway as well. So yeah, this is all complete under privacy.
So before we do the demo, we'll give a bit of an idea of what the future plans are for Starfall. This is very early stage work. And so just the technical roadmap for about a year will look like this. So the main priority is to foster greater interoperability between Nightfall and Starlight, Starfall being the first instance of this. A key development step for both of these is recursive proofs. It's been mentioned a lot in the ZK-EVM talk and in Mary's talk at the start of today. But recursion really is key to a lot of things. In Starlight, it allows us to have greater anonymity. And in Nightfall, we have greater efficiency. The eventual plan is to execute Starlight transactions themselves within Nightfall. This will reduce the cost of computations on Starlight significantly, and also allow us to use Nightfall state directly within the Starlight transactions. And finally, as Miranda's mentioned, Starlight is deployable on any EVM-compatible chain, but it's also deployable onto any EVM layer, so Optimism or ZK-EVM. Moving to Starfall, we want to ensure that we preserve the connectivity across all these multiple L2s as well. So I guess now is a good time to do the demo. At some point, the screen will change. Cool. So the idea behind this demo is to, let me just zoom in a little bit, is to try and show, or try and replicate a real-world business process onto the blockchain using the privacy technologies we have, so Starlight, Nightfall, and Starfall. The top part will cover the business process, and the bottom part will be how that maps to blockchain processes. So the first step here is to imagine a sort of network procurement agreement. So we have two main parties here. We have Alice and Peter, and they sort of organize a tiered pricing arrangement between themselves. That being, for SKU 001, there are various thresholds that you can see. So 101, 201, and various prices per unit. It's pretty simple here. The 101st item is going to be $90, and the 201st item will be $85. Otherwise, they're 100. And another key term in this agreement is that Bob and Charlie, who are subsidiaries of Peter, are also governed by this contract. And so essentially what we have here is we will register this contract on chain. What that does is create a commitment to this contract within the Starlight Outputs app. This isn't the same as notarizing, because what we'll end up doing is when we raise invoices or purchase orders against this agreement, we'll actually use information inside this contract to correctly adjust or reject purchase orders. So that's one layer of privacy in the sense that external parties who are not privy to this contract cannot introspect the terms of this contract. But there's actually a second layer of privacy here between Bob and Charlie. So Bob and Charlie are allowed to participate in the contract, but they're not allowed to see what each other has purchased, right? So we have two layers of privacy stored within the same commitment in one Starlight app. So now that we've registered the contract on chain, we'll raise our first purchase order in Starlight.
Yep, so in the tiered pricing Starlight generated application, here Charlie will first raise a purchase order to Alice based on the agreement that's just been committed to. Here he wants 100, and since it is the first order on this, the unit price is $100 per item. But remember that Charlie and Bob don't actually know what each other have ordered. So here, actually, any price changes that need to occur later will actually be calculated and enforced in zero knowledge in the invoice step later. So here we'll have Bob also raise a purchase order just to demonstrate the buyer's network. Here he will only want one. And again, here notice he puts a price per unit of 100, even though because Charlie ordered 100, he will actually be in the next tier, but he's not aware of that yet. So we'll see that later when the pricing is calculated properly. So similar to the way Nightfall does it, as we'll see, on-chain, the only thing that observers can see is a transaction hash and a commitment hash representing this purchase order, only if you have the key. So here, Alice will be able to decrypt and be able to see the key information inside, which here is the SKU and the quantity. And the SKU will refer to the pricing agreement that they're committed to.
Yeah, so now that they've both raised purchase orders, Alice can actually tell that there's two purchase orders for her, because directly on chain, she will see two tokenized versions of the raised purchase orders, or purchase orders that have been generated as part of this agreement. So we don't actually have any external sort of ERP or any kind of management system here. This is purely through reading private on-chain state. So what Alice's job now is to essentially fulfill these orders. So the first thing she's going to do is actually privately mint the relevant number of items. So typically this will be filled by an ERP automatically, but here we'll just sort of punch in some numbers. And the idea behind this is that Alice will do sort of just-in-time tokenization. So perhaps she has all these CPUs in a warehouse somewhere, and she realizes she needs to fulfill two orders for a total of 101, and she'll just directly mint these tokens. And just like in Starlight, we essentially have the public view, which is a couple of hashes and a zero-knowledge proof. But because Alice knows a private key, she's able to decrypt the contents and extract the metadata that we baked in before. So once she's minted the tokens, she can now start fulfilling the orders. So the first one she's going to fulfill is Charlie's. So what she'll do is she'll perform a private transfer, again in Nightfall, to Charlie. So what happens here is the UTXO that's created as an output to the mint circuit is then consumed entirely as part of the transfer circuit, where two new UTXOs are created, one under the ownership of Charlie and one returned back to Alice as change. So Alice gets back the change she made, and so this one has the value of 1, or the quantity associated with this token is 1. So now that she's done that, she'll be able to do her first Starfall transaction, which happens when she raises the purchase order. Raises the invoice.
So Alice will go back to the Starlight Zap and generate an invoice to Charlie. This is the first one that has been processed, so correctly, the unit price is $100 per unit, so the total is $10,000. And here, the Starfall aspect of this is that she uses a Nightfall transaction. So the transaction actually transferred the ownership of the goods, or the tokens representing the goods, to Charlie as an input to the Starlight circuit. As long as the quantities and the new owner match what is expected, and the transaction actually exists on chain, then it will go through. And the Starlight input here is the purchase order originally made by Charlie, so that is actually consumed. So this prevents Alice from ever raising more than one invoice per purchase order, so she cannot try and charge Charlie or Bob twice. Here as well, so we're actually generating the proof, so we're waiting for it, but she actually cannot charge anything else but the correct price. And again, like the purchase orders before, on-chain, it just looks like 2 hashes, but if you know how to decrypt it, you'll here see the SKU, quantity, and subtotal based on the original agreement.
Cool. So now that she's done one of the orders, Alice will do the other. So what Alice will now do is transfer that change that she received as the output of one of the transfers to Bob. So she doesn't have to mint anything else. She only has to mint once to fulfill all these orders. So as part of the private transfer, this will look exactly the same on-chain. So you can't tell, because they're fully zero-knowledge circuits, you can't tell who the recipients are, you can't tell what was transferred, you can't tell who did the transferring. So in this case, the transfer has gone through. We see that the output token is orange because Bob now owns it. And if you are Bob, you're able to tell that you've received the token with this metadata associated with it. So now that she's done that, she'll actually raise the invoice to Bob.
Yep, and so similar to Nightfall, this raise invoice function call is indistinguishable to the previous one as well. So to an outside observer, nobody knows that Alice is raising a purchase order, raising an invoice to either Bob or Charlie. Nobody knows where it's going or what the value is. It is just those hashes. But here, the key point of this is that the unit quantity is $90. So even though Bob has no idea what has been purchased in the buyer's network, here's that Charlie has ordered 100, he knows that he will be correctly invoiced. And that is enforced in the zero-knowledge circuit, and Alice cannot raise an invoice for any other value apart from the correct value based on the agreement and what has been ordered previously. So again, the Starfall aspect, so the Nightfall transaction input, is the transaction that transfers Bob ownership of the tokenized goods, and the Starlight input is Bob's original purchase order, which is consumed, so she cannot do it again. In consuming the original purchase order, we must have the same quantity and SKU as Bob wanted before. And again, as we can see, the subtotal and quantity and SKU is correct. And we can only see this if we have the key to decrypt it.
Yep, so at this point, we'll just follow Bob from here on. He essentially has purchased the goods from Alice, and he's retrieved the token that, or tokenized form of that good, but the goods themselves are still sitting, presumably, at Alice's warehouse. And so what Bob needs to do is organize some kind of freighting. So he goes to his freight provider, Frank, and the idea behind this is similar to the first one, which is that he has a separate agreement with Frank, right? And this isn't a tiered pricing agreement. In fact, it's much simpler than that. It's just a minimum order quantity agreement. And this is a completely separate Zap. So if you think about it, Bob is bouncing between different zero-knowledge applications that govern different interactions between different parties, right? And so in this agreement, it's just him and Frank, and it's a very simple one. So we'll register that on chain as well, so that it's a private commitment to those things. And then Bob will raise a purchase order to Frank.
Yep, so now in the separate Zap, because here we have a minimum order quantity logic when we raise purchase orders and agreements, compared to the previous one, which was tiered pricing. So very similarly, Bob will raise a purchase order. He just wants one pallet based on the committed to private agreement that he made with Frank. He will now create a commitment that represents a purchase order that will be sent to Frank, and Frank will be able to decrypt it once it's finished.
So now Frank realizes he needs to do something to fulfill this order. And what he's going to do is he's going to do something very similar to what Alice did. And he's going to, I guess, mint something that represents that freight. So again, this would normally be filled up by some automated process. We can just make up batch numbers here. But this could be a bill of lading. It could be something associated with the freight. But essentially, he tokenizes those documents or that instance. And then he's essentially left with a token representation of the freight. And what he can do with that is then transfer it to Bob. So he does a similar private transfer to Bob. And again, not only were the previous transfers indistinguishable when Alice did them, and the mint was indistinguishable, but all of these processes are also that. So you can't tell who has minted anything, who has transferred anything. It's all under zero knowledge. So once he's done that, he'll do the same process again, and he'll raise an invoice to Bob.
Yep, so back to this Starlight-generated ZAP. Again, Frank will raise an invoice, consuming Bob's original purchase order, and he is forced to use the right quantity, SKU, and price as well. Otherwise, the proof will not be generated. If he tries to use a different proof, it would not be verified on chain. And if he tries to use a transaction that has not occurred in Nightfall or is not relevant, then that will fail as well. So he is forced at every step to invoice Bob correctly, and Bob can be absolutely sure he's being invoiced the correct amount. And the Starlight info here is, again, the purchase order that has been consumed. So we'll just wait for the proof to generate here.
We're running a lot of applications in the background.
Yes, sorry about this, yeah.
All right, so thank God that happened. Right, so now that the goods, now basically at some point later, Bob actually receives the goods physically, right? So he has tokens that represent the CPU, tokens that represent the freight. At some point, the goods themselves actually show up at his door. Now, he might undergo some kind of quarantine process or quality assurance process once he's received the goods. But once he's done that, he may want to check the goods into his own warehouse. And to do that, he might want to combine some of these tokens, right? So you can imagine that in a more complex scenario, he might have many tokens and many different freight tokens as well. And so his idea would be to combine these or aggregate these such that he can sort of allocate landed costs or allocate ESGs or carbon to the incoming token. And then he doesn't have to manage the freight tokens as well. So what he's going to do is take as an input in Nightfall both the supply token and the freight token and output a variation of it. So it will keep the same SKU in the quantity. Maybe there's an internal batch number that he has a mapping to, so he doesn't want to use the manufacturer's batch number. So let's pick a different number. And maybe he wants to aggregate the freight. So it'll include both freights from the freight, both carbon from the freight and the supply. So performs a transform circuit in Nightfall. And he essentially gets, as an output of this, the same token he put in, just modified with modified metadata associated with it. So in here, we have a token that has 75 as the batch number. And as an input, we had a token that was slightly different with 55 as the batch number. So now that he's done this, the next step would be to pay people. So when he checks on chain in the original ZAP that he had with Alice, he can actually see how much has been invoiced to him and how much he has paid. So obviously, he was invoiced 90 from the invoice token that exists on that ZAP, but he hasn't paid her anything. And in fact, he will continue not to pay her anything because he's going to pay Frank first. So in the ZAP that he shares with Frank, he'll notice that he owes Frank 50, and he hasn't paid it, so he's going to pay that now. In fact, he's actually going to just mark that as paid.
Yeah, so in the ZAP governed by Frank and Bob, he will now pay the invoice that he's found previously. So this will consume the invoice, so it cannot be paid twice. And additionally, if Bob wanted to pay Frank with cryptocurrency or something that is tokenizable inside Nightfall, then he would be able to use a Starfall transaction here, which uses the transaction hash as proof that the transfer has been made, and then only could he mark as paid. Here he's just paying in fiat, so this is an accounting measure for Frank to show that he's actually paid the invoice.
Yeah, and if he goes back to the contract, he'll actually see that, right? So he'll see that a certain number of invoices have been nullified or consumed as part of being marking them as paid, and that'll show up in the ZAP as well. So there can be no dispute as to what has been paid and what has not been paid, or what has been raised in invoice and what hasn't. At this point, Bob is free to use those goods in a different process. And so let's say for a minute here that the CPU forms part of a bill of materials, so part of a manufacturing process. Obviously, there are more materials that go into here, but to keep it simple, we'll just have a single CPU. But there may be additional costs, so machine costs, labor costs, that aren't necessarily tokenizable. And what he'll do here is he'll use another circuit that looks very similar to the previous one he did, which allows him to alter the metadata again in a verifiable way. So in here, let's say the SKU for the phone is 99. He's just going to mint or transform one of them. You might have an additional batch number for this, so let's call it 90. And he might have some carbon that's emitted or aggregated as part of the process. Let's call it 750. And he'll modify the token. And the key in doing this is that we end up with a consistent and verifiable way of how the token is flowed and changed over time. This is very useful when you want to audit the process, or if you want to prove to an external third party about the nature of how a token came to be. So here he's outputted essentially a phone. And if you check the metadata, it would be what we assigned it to be. So at this point, Bob has essentially manufactured some products, some finished goods. And what he really wants to do is that when he eventually sells this product to a customer, so when a customer physically buys a physical phone, he'd like to do this thing where he gives them a public ERC-721, so a public NFT that is associated with the phone. And that could give them access to specific things or special areas, but also he could expose to them this history, so this provenance for the phone or the components that went into the phone. The catch is he's actually going to try and sell it to someone in the European market, and Richard, the regulator, has set up some certain rules that he must prove, or Bob must prove, that the phone is below a certain threshold from an ESG perspective. So in this scenario, Bob wants to prove to Richard that he meets those criteria. So the first thing he's going to do is actually he's going to burn the token that represents the phone that he just created. And a burn process is essentially the inverse of the mint process, whereby we can privately consume a token in Nightfall and not generate an output one. This is useful in certain scenarios where we want to prove that we've verifiably destroyed something. And now we go to our third ZAP.
Yep, so in the ZAP generated by Richard the regulator, here he will take in that burn transaction created by Bob, and he will be able to extract all the metadata from the token. Here he can, as Elias said, check that the CO2 value is within an expected threshold and do other checks as he wishes. Then it will be separated into CO2 value and the phone token itself. So this app also actually mints an NFT of the phone, completely separate from the CO2 value.
Cool. So at this point, he's publicly minted something because someone has purchased it, right? So what we're able to do is check out the contract that Bob has created to support the NFT contracts that back the physical phone. So in this case, we have a contract address and a minted token ID, and we'll quickly jump into MetaMask and try and import it. And hopefully we would have bought it. And so we're able to, since we connected everything up to Ganache, we're able to connect the NFT contract directly into MetaMask. And the token ID here, we can derive it programmatically from the phone that was, or the token that was burnt, or we can just generate it randomly. It's kind of OK either way. And at this point, Richard might want to see the ESG values. Perhaps it's publicly stored in the contract that Richard created. And if we go and inspect the ESG contract, we'll find that associated with Bob is 750 units of carbon. And if we check where that value comes from, it actually comes from the carbon value stored within the phone token that was burnt, right? So we have this nice continuity using Starfall across the various layers where we're able to bridge it. And so in summary, we've kind of been able to map this entire kind of semi-complex business process to a range of circuits, zero-knowledge circuits that happen both in Nightfall, Starlight, and eventually utilizing Starfall as well. And that's the end of the demo.
Great, thanks, guys. That was fantastic. I think you're pushing the envelopes of cryptography. Everyone will know about Alice and Bob, but when you get down to Richard the Regulator, you've really hit the sweet spot. Now, this is something that you could not do without ZKP. Well, you could, but you'd be out of business in a week because everyone would know who your suppliers were, what you were paying them, everything. So you need ZKP, and actually the huge benefits it gives you from enforcing correctness means you don't have a department phoning people up and saying, where's that invoice, or you've calculated that price wrong. It's guaranteed to be correct. It's fantastic. Now, we've got a couple of questions for you, if my eyes can just tune into them. So the first one is, does a Starlight ZKP employ a collision-resistant hash?
Yeah, I can take this one. So yes, so Starlight will automatically create a zero-knowledge application where the commitment system essentially governs the privacy and the integrity of creating a new state. And this commitment system is based on the Poseidon hash, which is indeed collision-resistant, similar to Nightfall as well, I believe. Yeah.
OK, and the second question is, if Bob wants to return an order or part of the order, then how would that play out?
Yeah, so that's a really good question. It's one of those things where business processes tend to be more flexible than what we've shown here. The answer to that, unfortunately, is kind of it depends. So a lot of the circuitry that we use as part of Starlight and Nightfall is kind of dependent on what you want to achieve, right? So in this scenario, we have it such that the volume is considered done when it's transferred and the invoice is raised. Obviously, there could be processes where that volume is only considered, I guess, incremented once it passes some kind of QA/QC, section where the recipient, in this case Bob, was kind of satisfied with the quality of the product, right? If you wanted to do returns, essentially, probably the simplest way will be to track, I guess, two boundaries. One is being what you owe and what you've returned, and then the difference between the two being what you have. So that would probably be the most straightforward way to do it.
Great. OK, well, thank you very much, guys. That was incredible. So we're going to take a break in a moment. We'll be back soon, where we will be talking about how you should use technology to meet the needs of Richard the Regulator. Well, welcome back, everybody. In this next section, we'll be seeing how we can use technology to help us with regulatory issues and related things like that. Very much as I said earlier, very much a topic of the day with things like Tornado Cash happening. We need to make sure we're on the right side of the regulator. So up to now, you've had the benefit, I think you'll agree, of some really insightful and cutting-edge thinkers. I'm afraid that that all changes now because you've got me for the next section, and I wanted to talk a little bit about decentralized authentication. So let's dive straight in. So here's the title. So I'm actually going to pause on the title slide and say, what do I actually mean by decentralized authentication? Well, I think for authentication, there's lots of definitions of authentication, but the one I'd like you to think about is it's about you verifying some claim that I make about myself and being able to do that. So, for example, if I claim to be the carbon-based life form Duncan Westland, you might use my passport as a way of verifying that. More typically in the world we inhabit, I would claim to own a public key, and you would be able to verify that by getting me to, by sending a challenge and getting me to answer that challenge with my private key. Now, there's a bit of an issue here if we're talking about decentralization, because the fact that I've got a passport, the fact that I've got a public key which you trust, actually means necessarily that somebody who you trust has given those things to me. And the problem with giving me something is, if you're in a position to give me something, you're automatically in the position to refuse to give me something. You have the ability to censor, and that is not decentralized. So the question then is, how can we use this lovely decentralized blockchain, but actually authenticate people when we need to? And I'll talk a little bit about that in this presentation. Okay, so before we dive in, just to say, there is a little bit of cryptography in this, but if you're comfortable with certificates and signatures, and I'm assuming most of this audience is, then you should be fine. If you know a bit about ZKP, that's also fine. But it's actually not necessary. You can manage without that. There's also a disclaimer here, which our lawyers made me put in, so that's fine. You can read that at your leisure. It does actually, though, usefully point out that Nightfall is completely open source. It's public domain. You can use it as you like. We'll be talking a little bit about Nightfall as part of this talk. Okay, so with that in mind, this slide is actually just a brief aside. I just sort of wanted to cover quickly what Nightfall was, just in case you hadn't already picked that up. So Nightfall is EY's solution for transacting privately on an Ethereum or Ethereum-compatible blockchain. That's what it does. It provides scalability as well as privacy, so you can do those transactions for actually a very small amount of money, about a tenth of what it will cost you to do a normal ERC20 transfer. It's deployed on Polygon Proof of Stake and the Mumbai testnet, so you can use it straight away if you wish to. It's interesting to see how it kind of fits in what I call the hierarchy of scaling solutions. Elias, my colleague, came up with this, but I like it very much. So if you think about scaling solutions, the first question to ask yourself is, where's the data? Where's the data I need to synchronize my node up to this layer 2 scaling solution? And it could be on-chain, in which case that's great, because I'm guaranteed that whenever I fire up a node, I can synchronize it. Or it could be off-chain, much more data efficient, but I'm reliant on a third party to do that synchronization. So sticking with on-chain, you then really have kind of two ways of doing scaling. I would suggest either a ZK, well, actually just a snark way of doing it, or a Stark way, or any of those cryptographic approaches, or you can do it optimistically, where you put something on chain, just asserting that it's correct, and you leave it to other people to create a challenge if it's not correct, and then that challenge is played out on chain, and we see who's right. They both work. They both have pros and cons. I don't want to get into those today because there isn't really time. And then right at the bottom, this would represent the privacy layer. So you can see you could have a ZK approach. You know, Aztec, classic example of that. You could have an optimistic ZK approach, and that's where Nightfall fits in. It has an optimistic layer for scalability, has a ZK layer for privacy, and then you can have solutions that actually don't use privacy, but they're generally more flexible in what they can do. Okay, so sorry, that's a bit of an aside, but you know, if you don't know what Nightfall is, the rest of this wouldn't make a lot of sense, I think. So let's think about a blockchain. Okay, so you have two things that you might recognize. You have transactions. That's account A sends 10 tokens to account B. That's a transaction. Everyone gets that. Transactions can, well, by default are public. They've always been public on public blockchains, hence the name. But of course, as we now know, ZKP technologies give us the option of making those transactions private. So it could be public or they could be private these days. Think about accounts. These are the addresses that are controlled by people, by smart contracts, by organizations, which hold your money, essentially. These can either be anonymous. They could be anonymous in the sense of it's just an Ethereum address and you don't know who owns it. Or if you're using ZKP, you might get a stronger guarantee than that of anonymity. We're not going to worry about that difference for this discussion. We're at a much higher level than that. Or you can choose to identify an account. You can say, this is my account over here. If you've enjoyed this talk and you'd like to send me a tip, this is where you send it to. Both have their uses. Now the great thing about having two dimensions like this is, and any consultant will tell you this, you can plot it as a sort of Boston Consulting Group type 2x2 matrix, also known by engineers as a graph. This is a kind of binary graph. You can just be in one section or another, but it's interesting to think about what fits in each of those sections. So let's start with the easiest one. We have public transactions and we have anonymous accounts. That is the headspace of Ethereum, or actually any other blockchain pretty much. But I'm talking about Ethereum compatible blockchains here. I think everyone would recognize that. That's fine. You can, of course, use something like the Ethereum name service. Here's an example, westlad.f. That is, by the way, where you should send your tips to. And now you've identified yourself. And you saw, I gave you an example of a use for that just a moment ago. So it has its uses, can be valuable. It can be valuable also when you want to do something like you want to show the provenance of something and you want to do it in public. You want to say, this is where that wine bottle came from, for example. Okay. Now we get into the darker regions. So in this corner, we have anonymous transactions, and they could be strongly anonymous. Anonymous accounts, strongly anonymous, and private transactions. Now, this is the world of Aztec, Zcash, Tornado Cash. they really gives you strong, and I mean, you know, cryptographically strong guarantees of anonymity. And actually, until quite recently, that's where Nightfall lived as well. But it's interesting to consider this square, where people are identified, but their transactions are private. In Web3, there isn't really, I would conjecture, anyone occupying that space. But recently, we've re-engineered Nightfall, so it sits squarely in that space. And I'll come on to why in a moment. Okay, so hopefully that's clear. We'll make quite a bit of use of this matrix, so right, let's move on to the next slide. Now, imagine you're doing a transaction. You're a business. How sure are you of the counterparty that you're transacting with? Because you better be sure, because actually the regulator probably insists that you are sure. Well, let's see. So if we are in the public and anonymous space, you can do a few things. You can check that you're not interacting with somebody who's on a sanctions list, like the Chainalysis sanctions list. You can see the entire transaction history, so you might actually be able to work out where your counterparty's money came from. It's not too bad, actually. If they're identified, you have a little bit more assurance, because you can make checks so that, say, if you have westlad.f, you could actually make checks that I really do own that account. And so you would have now a really strong idea of who you were dealing with. If you're down in the private anonymous space, well, you know, it's zero knowledge for a reason. You don't have this information. You don't know who you are dealing with. In fact, it could be perfectly possible for you to receive money and you don't know where it came from. That can be engineered. So this is a really hidden space. Now, I'm not saying that doesn't have utility. I'm just making that point. And finally, up here where you're identified. Now, this is quite interesting. Because you can actually still do things like check for sanctions lists. You can do a bit of KYC on the account holder. You can check that westlad.eth is an honest person. So the ability to identify an account really helps when you're doing regulation, or sorry, when you're doing things that need to be okay with the regulator. Okay, so let's ask ourselves the next question: what would it like to be? What would it be like to do business in this scenario? Okay, anonymous and public. So here we are transacting our business on the Ethereum blockchain. Well, actually, that's a big problem because all of your competitors can see exactly what you're doing, pretty much. I mean, yes, you have an anonymous account, but actually it wouldn't be too difficult to de-anonymize. And then you can start to see what I'm paying for things. You can start to see who I'm buying things from. This is not a world in which you can often do business. You necessarily have to hide things from your competitors. If we identify ourselves, well, we've kind of made it even easier for our competitors, haven't we? Because we've actually saved them the trouble of having to de-anonymize an account. So I'm not saying there are no use cases here. There absolutely are. You know, to take my earlier example of tracking wine bottles or whatever it is, this might be the place you wanted to operate, but it's not the normal place to operate. Down here, well, you can certainly run business down here because all your transactions are private, you're anonymous, none of your competitors can see what you're doing. Brilliant. The only problem is you might struggle to prove to the regulator that you're doing the right thing. And we've seen that happen, haven't we? That's played out in real life in the last year. So, yes, good for business, sort of, but it's not good for a business that wants to show that they're doing the right thing, I would suggest. And finally, we come to this last square. Now, this is interesting because if you think about it, moving aside from Web3, this is where actually everyone does business. Well, apart from a few drug dealers, this is where people do business. Think of EY. You don't know how much profit EY made on a particular audit job. We won't tell you that, because if we told you that, our competitors would know and they'd be in there with a lower quote or whatever. But, you know, everyone knows that EY is doing audit work. That's our business. We're not a secret organisation. So this, and you could say that to about any business, any regular business, I would suggest. So all business is actually done in this square. So if we want to work there, and it seems to be great because we can show regulatory compliance, we can actually do private transactions, so we can behave in a way that we're used to behaving. So how could we actually bring that about? How could we design a Web3 application that can work there? Okay, so here's a way I would suggest you don't do it. So you could have your ZKP layer 2 system, a load of smart contracts probably. That's certainly how Nightfall works. It's certainly how most of them work. And what you could do is you could put a contract in front of it, an allow listing contract, and you could say, I'm not going to let you move money into the layer 2, or any token come to that, if I don't know who you are. You have to prove to me who you are. I'll put you on the allow list, then you'll be able to transact. So implicitly, I'm going to do some sort of KYC, know your customer, work on you. And now that's a bit of a problem, isn't it? Because it comes right back to the start of my talk. If I can put you on an allow list, I can decide to not put you on an allow list. So what does that mean? That means we're centralized again. That is not what we're about. If you want to build centralized applications, generally speaking, there are easier ways to do that than using a blockchain. You might think, well, okay, yes, but what if I don't just have one person making this decision? What if I have something like DAO, you know, so I've kind of distributed that decision making? Well, that's better, that sort of works, but it's actually really hard to think of a way to incentivize the members of that DAO to actually act in the right way. I mean, how do you pay them to decide whether somebody is an appropriate person to transact or not? It's actually a very difficult problem. I think the way we solve that problem is with X509 certificates. So good old X509 certificates that have been around more or less since the dawn of the internet. Now, most of you will be familiar with these as SSL certificates, such as one might use to assert that you're amazon.co.uk. But there are other flavors of X509 certificates. One of them is called an extended validation certificate. And this is the sort of thing that would typically be used by a lawyer or a doctor, maybe to sign a PDF to say, yes, I signed that. That in most jurisdictions, certainly in Europe and the US, if it's done properly, will have legal force. It's the same as a wet signature. So actually, this is quite a strong way of knowing who you're dealing with. Another similar sort of certificate one might consider is code signing certificate. So if you're a developer, you create some code, you want to run it on Microsoft Windows, you will be given a developer's certificate that you can use to sign that code. And if you have one of those, it'll run on a Windows machine. If you don't have one, it won't, at least not without a lot of warnings. So these certificates are actually very strong guarantees that you're dealing with who you think you're dealing with. Well, that's all very well. We'll talk about how we get them in a moment, but I've got an X509 certificate here, and I've actually, by the way, got the private key that goes with it. How does that map to a blockchain? They're very different things. What we can do, and what we have done in Nightfall, it's in the code base, you can go and have a look at it, is we can actually write a smart contract that can validate an X509 certificate. And further than that, it can tell you if it's the right sort of certificate. So it's not just you know, an SSL certificate for a website. It's one of these much stronger extended validation certificates. So that's the first thing. You can give it a certificate in sort of binary form. It'll chew through it and it'll say, yeah, this certificate's valid. Brilliant. Should I whitelist that person? No, because certificates are public. Anyone could have put that in. So there's another check it needs to do. It needs to check that you actually have the private key that goes with that certificate, so it will get you to sign your Ethereum address. This is very useful because it now says, I'm Duncan Westland, I'm authorized, and here is the proof. Oh, and by the way, this is my Ethereum address because I've signed it. The contract can check all that, and if it's happy, it can add that address to the allow list, and you're good to go. And you'll continue to be good to go unless you revoke your key or your certificate expires, or indeed you end up on a Chainalysis sanctions contract. This seems to be a fairly democratic way of accessing layer 2 privacy. Now, we should turn our thoughts to how you get a certificate, because, of course, if we're not careful, we'll just end up in the same situation we were in before, where the person who gives you the certificate can decide not to give you the certificate and you're centralized again. But the great thing about certificates is you can get them from lots of places. You know, Entrust we saw on Tuesday, DigiCert, various others will issue these certificates, and they will have a set of checks that they go through. You know, if it's a certificate for a company, is that a properly formed company in a particular jurisdiction, not in North Korea? If yes, you'll get a certificate. If no, you won't get a certificate. And they're very careful about it because their whole business depends on that reputation. So this is quite good because it's pretty close to being decentralized. If you're a bona fide organization, you have lots of people you can go and see to get one of these certificates, provided the X509 contract actually knows about the root of trust that CA uses, and we can put them all in easily, and provided it knows about all the certificate policies and things that actually identify it as being a certificate from that authority of the right type, then we're good. You can go and get one. If you're a bad actor, you won't be able to get one from anyone. You could actually also have one of these CAs issue an intermediate CA certificate, and then you can, as an organization, use it to provision your employees. This is a way, I think, where you can get the value of operating in that top left-hand corner with maybe not perfect decentralization, but for all practical purposes, good enough decentralization. So that's actually how Nightfall works. If you want to interact with Nightfall, you'll have to get one of these certificates, because otherwise it won't let you in. So what are the implications of this? Well, you do lose some privacy for sure. So if EY was working with one of these certificates, everyone would know that EY had moved tokens, coins, whatever, into Nightfall's layer 2. But once they've done that, the transactions would be completely private. So this is very close to the sort of way that the organization normally works. Third parties have no information about the transactions that we make within layer 2, so that's unchanged, nothing's exposed. And an auditor actually could see all of those transactions with the cooperation of, to take my example, EY. So we have the choice to de-anonymize those transactions if that is required by an auditor, by a regulator, but that remains an off-chain private thing between the auditor and the organization. So that is what I think we should be doing. I hope you agree. That's the end of my talk. Well, almost the end of my talk. I have a few final thoughts. I think I've mostly covered this, though, actually. But we have a few questions, or one question. So the question is, could private and identified be considered CEXs, identified users, but private transactions that can't be seen on the outside or by users within? If I knew what a CEX was, I'd be able to answer that question, but I don't. Any others? No, I think we're done. Okay, well, in that case, thank you for taking the time to listen. And we'll move on to the next talk. I'm going to introduce an old colleague of mine. I mean, he's young in years, but old in acquaintance. This is Mr. Arwin Holmes. He is our Chief Technology Operating Officer. And he is going to give us a jolly good talk about tokenization and scaling. So welcome, Arwin.
Duncan, always a pleasure, sir, and sorry I could not be there with you in London. Is my audio coming through okay?
Yes, it is, yes. And we're sorry you're not here as well.
Excellent.
We'll ship you in next time.
Yes. Well, good morning, good afternoon, good evening, everyone, wherever you might be tuning in from. It's been an amazing Blockchain Summit week. As Duncan mentioned, Arwin Holmes has been one of our emerging tech leaders here since EY started this blockchain journey. It's been a pleasure working with our amazing team. Last 3 years have been heavily focused around helping many of our clients on their digital assets journey. So in the next 30 minutes, I'm going to be hitting on a few hot topics, as Duncan mentioned, touching on tokenization and scaling the ecosystem, particularly around adoption. And in the past few years, when digital assets really came into view and traditional finance started to lean in, the emphasis on foundational enterprise capabilities was predominantly around custody. How do I hold and safeguard these assets that are already out there? And now that those foundational capabilities are starting to mature, today it's about getting new assets of value onto these new rails. And we're doing this through tokenization, and we also need to enable this at scale. On the scaling piece, in Ethereum, the last push has been really around getting to proof of stake with the merge. And last year, a really notable achievement, and then most recently with Chapella, now enabling withdrawals, we're nearly there. So we'll touch on some of what needs to come next. And as the technologists and builders here in this audience, we'll also first need to understand the why, which many of us also touched on in the last few days. So this might be a little bit of a review, but I think it's really important as the ones building the solutions. So just as Duncan mentioned, I think there's a bit of a disclaimer. I'm not sure if my clicker is working here to advance the slides. I might need some help. Can we get next slide, please? Yeah, so quick disclaimer, I think we can move past this into the content. So we've all heard the buzz. The rails are continuing to evolve. Many of us are very bullish about tokenization for a variety of reasons. So fractionalization, extended reach, either in the form of liquidity or democratized access. Financial inclusion is a big thing. Efficiencies through on-chain automation and so on. And if you have something of value, whether that's a digitally native asset or a physical one or some right or entitlement, you might consider tokenization too. But what does it actually take to tokenize? Well, this will depend on a couple of things. So first, what is it that you're going to tokenize and where does it make sense to do it? So what assets, what rails, what jurisdictions, and a whole host of other considerations. And then after we cover that, then we can get into the how. What helps us at EY when we're delivering solutions like this is we find popular frameworks like IDDS, which you'll see at the bottom here: identify, discover, design, develop, and sustain, coupled with an agile way of working, is really the best way for us to move quickly along this path and address all of the changes that are evolving alongside us as we move. Jump ahead to the next slide. Some of the strategic considerations here will vary considerably. It's going to depend on the demands of your customers and the opportunity to your business. Many financial organizations, as we heard in earlier days, are starting with tokenized cash or deposits, enabling better payments. It makes sense as a place to start, given that most other financial instruments have cash components. And many non-financial organizations are starting with things like NFTs or on internal use cases as we try to get more regulatory clarity, or things like customer loyalty. Now, whatever the use cases are, there are a few key factors here to consider. Thinking about what you will tokenize, assuming we're tokenizing most things, what you will tokenize first. The first consideration or factor is really around simplicity. So how simple is this to execute technically, operationally? What are the standards that exist already and how well adopted are they? The effort to tokenize a currency versus a syndicated loan or another complex product, for example, those things could be quite different. The second here is around utility, and this was touched on the last few days as well, but how useful will this be for your organization, not just you, but also your customers and your ecosystem, and what other use cases are going to be unlocked by making this token available. And then as a theme of what we're talking about in this segment today, regulatory compliance. So what clarity exists around this type of asset that you're going to look to tokenize? For example, we heard from John Whelan on day one that if you intend to fractionalize your tokens, then you probably should consider getting a securities lawyer, because that's probably what it's going to be viewed as. And Duncan hinted at this earlier today, that if you intend to put all your terms and conditions in public view or your competitive advantage, you'll likely not have a viable business for very long. So we'll still need to find this balance of privacy for commercial sake and regulatory compliance. Now, after we've defined the what we're going to tokenize, we still have to answer this question of where, right? And we should think about this in these two dimensions. One is the rails or the networks, and the second is the jurisdictions. So if we look at the networks, if you're tokenizing, the rails are going to likely need to support smart contracts because that's how you're representing your tokens. So how easy is to code those smart contracts on those rails? What sort of dev support do you have? What sort of community exists? And what ecosystem providers are available to you to aid you on your journey? And these are just a couple of considerations, and we at EY have a framework of 30+ criteria that we look at across product, tech, and risk dimensions, and when we're assessing various protocols to support our clients on different use cases. The next where question is really around jurisdictions, and as we've heard earlier, significant differences across countries and regions when it comes to the treatment of digital assets. And beyond this digital asset regulation, we're also going to need to be mindful of broader regulations around data, particularly around residency and consumer data privacy, so things like GDPR. So stating the obvious here, but please do not write sensitive data or data that needs to be changed or deleted at some point in the future to a blockchain. Right? Some of these are longstanding best practices, but I know people might be tuning in that are just starting their journey. Last but not least, it's also important to note that not all assets are supported on all rails, and each rail has a different network and a differentiated reach. So the answer that you might arrive at may involve multiple rails and jurisdictions, right? It might not be just one. So great, now that we've defined the what, the why, the where, we can start to get a bit into the how. So if we go into the next slide here, we're going to talk about designing for tokenization. So whether you're building this yourself or buying or partnering with a myriad of technology providers, make sure that you're building for the long term. I'm not seeing the slide advance. If somebody could help me out on the designing for tokenization slide. Thank you. So there's a myriad of technology providers that you could leverage, right? But regardless of your approach, right, make sure that you're building this for the long term. So one, leveraging open standards and building in support of the largest rails, even if you might be starting small and private today, this will give you the most reach and the most flexibility long term. That's going to allow you to scale with the industry. And unless it's really a core value proposition to build and own a component or a piece of infrastructure, you should really consider integration with other Web3 providers that are doing the same and building for the long term. My personal concern here is that we don't go back to the early 1990s building specialized web pages against pseudo standards that worked on certain web browsers. Achieving cross-browser compatibility was a nightmare for many web developers in the early days of the internet, and that's something I think many of us have learned, but we can avoid as we build in Web3. And last but not least, remember, this is a team sport, and the above is really critical for us scaling the ecosystem for enterprise adoption. And now as we move from these core design principles, we move to solution development. It's worth raising something that we've covered, and please advance slide. It's worth raising something that we've covered in last year's summit, and that's really that large parts of this architecture are not new. Apart from the things that are highlighted in gray regarding the architecture, all the blockchain bits, we can see that blockchain is really just another tool in our technology stack. We know how to build enterprise solutions for ourselves using service-oriented architectures, building API first, and so on. And much of the application development remains, except perhaps for some of these new compliance systems and third-party relationships. As we advance here, jumping into the blockchain's bits, next slide. Some of the core blockchain infrastructure components to start with would include things like wallet infrastructure, which we'll have highlighted in yellow for wallets. And then this is really the piece that's managing your private key management, integrating with internal or external providers. It's the component that supports your transaction building, your signing, your broadcasting. And the second core component is really on the node infrastructure. So here is really the internal and external node providers that are providing access either to internal networks or external public networks. Again, your Rails might involve a mix, and this is really the area where you have that connectivity. Now, if you're doing all of this interacting with existing blockchain infrastructure and tokens, that's all well and good. But if you're going to be inserting new tokens into the ecosystem, doing things like building a tokenization engine or a factory to create your own, there's a couple more components that you'll likely need to consider. And this could go quite broad, but I'll just touch on some of the critical ones that we see as table stakes for many of our clients. So we advance to the next slide. First and foremost, again, depending on where you're on your journey, for example, if you've already established foundational custody capabilities, you'll probably have some of this in place already. But if not, there's quite a bit to do. So here's an overview of some of the additional components that you'll need to support your enterprise tokenization capabilities. And I'll highlight these in yellow as well. So the first one here is really the tokenization engine. This component is really responsible for your smart contract management because tokens are represented by smart contracts. This includes things like deployment, combining your smart contracts, and the maintenance of multiple token standards. This is also the application that helps you manage your smart contracts, and it may also involve incremental updates to your existing software development lifecycle. There are special considerations for smart contracts because when they're deployed, like other transactions that go on a blockchain, they are immutable. So you'll need to have your upgrade patterns defined in advance. And so that these are additional considerations, when you need to update your DevOps processes, for example, in the environments that you might need for testing. Great. So if you advance again here, the next component that we'll highlight is the enterprise integration service. So this component supports the interface between your enterprise applications and the new digital asset systems that you may be setting up, including your wallet or custody solution, the tokenization we just discussed, and any underlying blockchain functionality. Could we please advance slides? Great. We'll step through one more. Next slide, please. So this next one is really the policy engine. Sometimes this is a last minute consideration. Things companies sometimes think of this late, but it's critical for maintaining compliance. The policy manager component, which helps to define and manage the rules and thresholds for executing transactions and supporting broader governance across all your digital asset operations. So things like smart contract deployments, who's allowed to do those or not, setting things like transaction limits, defining co-signer roles and quorum thresholds, also things like supporting the adequate segregation of duties across your digital assets organization. Those are all key. And then properly configuring the policy manager to help mitigate any potential risks to your business is really super important. And again, as people are building out more capabilities around digital assets, it's important that they have a policy that is spanning across all of those operations. So this helps us do that. If I look at the next one, the next component is really hinting at some of the challenges that we see with blockchains, and that they're not really great databases, right? When it comes to being able to pull data out and query data against the blockchain, it's really horrible at that. So you'll need to employ some strategies to enable enterprise data feeds. So this enterprise data feeds component really gives you the access to relevant data from the blockchain. If your tokens are digital representations of other value constructs, like if operations can't be executed purely on-chain, it would allow for things like reconciliation. Ideally, we try to move more of the assets so they're natively on-chain. I appreciate the differentiation and experimentation by JP Morgan and calling out deposit tokens, because this really allows us to remove these extra steps regarding reconciliation. But there's still cases where you're going to need this, right? If you are representing something in the physical world through a token, you're going to need to reconcile those. And that means you're going to need to pull data from the chain. A number of cash tokens on blockchains will need to match reserves that you're holding. Product tokens ideally should align with the inventory that's sitting at the warehouse. And beyond these, it can also support things like analytics, visualizations, reporting and tax, corporate actions, and many other enterprise functions. So following the enterprise data feeds, the next one is the orchestration service. And this component really acts as an abstraction layer on top of node infrastructure. So it's responsible for things like event streaming, read-write capabilities on-chain, storing on-chain data in off-chain databases, and powering components like the enterprise data feeds I just discussed, as well as ETL functionality, so supporting things like data transformations. You might get it off the blockchain in one format, but what you need it in is in a different format when it goes to other systems. So this component can help with some of that. Now, this might be overkill if you're only leveraging a single blockchain. However, if your resiliency plans will likely require you to have more than one node infrastructure. And your systems also may need to interface with more than one set of rails. So this orchestration service starts to become more relevant in those scenarios. Great, so I think that highlights most of the components I wanted to touch on in tokenization. If we jump ahead to the next slide, I wanted to emphasize for your enterprises that what's new here isn't the stuff that we do inside of the enterprise, right? It is really this yellow box, it's these ecosystem rails. And we need to continue building for these ecosystem rails, the shared infrastructure, in order for us to scale. So my call to action is, as a technologist here, the builders, what exactly is shifting from the enterprise to the ecosystem level? Again, hint, it's the stuff that's in the yellow box. So how do we represent value in a standard way? We know that shifting from a single enterprise to networks of enterprises via tokens, it's a bit more complex. But we might also consider contracts governing the movements of tokens or terms and conditions. Ideally, that we also have shielded with privacy to be another shift. And we can also represent those as smart contracts. One last one is a challenge, and really segue to my next topic is how do we hold and safeguard and transact this value? We do this through varying custody solutions today via digital wallets, plugins like MetaMask or Rainbow. This is on a similar path as well. And this is something that we need to look at a little bit more, right, to continue to scale the ecosystem for adoption. So this brings me to my next topic. If you could advance the slide again. I'll touch on what I mean by scaling the ecosystem, and we'll touch on some of the challenges in Ethereum today as the largest smart contract enabled protocol community. So following the widely successful shift to proof of stake, including withdrawals post-Shapella, I'm just going to call attention to another item here on Ethereum's roadmap, and that's account abstraction. And as a bridge here from the tokenization topic, you have great examples of on-chain controls at the asset level for tokenized assets. You could go pull up the smart contract on Ethereum for a USDC. You can see that there's potentially abilities to freeze those assets, to have whitelists defined, to have blacklists defined, to have restrictions on transfer. And again, we have all this at the asset level, but we don't really have those on-chain abilities at the account level today. So to explain this, I'm just going to start with some of the Ethereum challenges, right, and how that's working today. And this also is a challenge with broader industry. Save a few other layer ones that have already built in account abstraction as part of their core protocol. So today we really have two types of accounts. So you have smart contract accounts. These are addressable accounts. That's when you deploy a smart contract, it gets an address, and that's how you interact with that smart contract. And the other one is what we call EOAs, or externally owned accounts. These are accounts that users like you and I would have. And this is really the only way in Ethereum to start a transaction, or to call a smart contract for that matter. It's got to start with an externally owned account. Having this set up this way, currently it makes it really hard to batch transactions. It also makes it really difficult to manage gas. Gas needs to be available. So if you're doing this on Ethereum, you need ETH in your EOA in order to finance any transactions you're doing. If you have private keys, you have private keys to this EOA, you can really do anything within the rules of the EVM that's allowed for that address. And then if you don't have those keys, you really can't do anything. Lastly, if your keys are lost or stolen, those accounts are also permanently lost, right? And the other terrible thing is that if they're stolen, the entirety of the assets that you have sitting on that externally owned account are also put at risk. Hence the phrase that we've all heard, especially in the events of the past year, not your keys, not your crypto. So with account abstraction, this really gives us a better way to solve for these challenges, both on the user experience level as well as the security level for accounts. So, and there's really three ways to approach this. The first two here involve changes to the protocol itself, and I think would be less likely in the roadmap for Ethereum, just given the protocol changes that have already happened. There would be a long road for that. But the first two might be upgrading the EOAs themselves to be controlled by smart contracts. So you could have a contract basically proxy to an EOA to then do things to support account abstraction. The second would be to upgrade smart contracts so that they can initiate transactions as well, not only the EOAs. And then thirdly, it would be setting up a separate transaction system that would run in parallel to the existing protocol. And optimally, this would not necessarily require an update to the underlying protocol. You would still need a separate system for this. And this is an approach that some have taken in the ecosystem. It's important to note here that when we're talking about account abstraction, that this is really meant to extend support for what we call smart contract wallets as an open standard and offer a better way to manage the self-custody user experience. So getting away from having to deal with seed phrases and management of your and safekeeping of your private keys is kind of the only way to deal with externally owned accounts. So if we advance to the next slide, I'm gonna try here on my clicker, I'm not sure if it'll go. It's like it's not, might need some help here in moving this slide across. So if we touch on the benefits, the best example that I can touch on here is that I've used to wrap my head around account abstraction and the value that it's presenting is really what we have today when it comes to credit cards. So you can think of a credit card as effectively, this is my wallet to access my credit on a given card network. So with smart contract wallets, we can also have things like account recovery. You know, if you have lost your private keys, maybe you have another set that you can use to reclaim access and get that account back. That might be something you can do through multiple signatures or multiple devices, but there isn't a one item single point of failure that if you lose these keys, you're done for. So the other is around flexible gas management. I touched on this a little bit earlier, but today you really have to have gas in your externally owned account in order to transact. Using smart contract wallets, you could have rules set up where someone else pays your gas, or you pay someone else's gas. You could also have it set up such that maybe the decentralized application that you might be interacting with covers the gas costs on your behalf, right? And it still allows you to transact without having that gas necessarily in your wallet. So this kind of gives us more opportunities for dApp and wallet developers to further innovate on the user experience. The other thing I think that's really useful and helpful for the user experience is that it will allow things for like transaction bundling or batching, even doing something as a single swap. You have to do a proposal, an approval to confirm, right? In order to execute a swap, there's usually multiple interactions if you're doing this via MetaMask web browser plugin, not a great user experience, right? So whether that's that, or maybe it's a decentralized game application, you're able to pull transactions together and we can be more efficient about how we're leveraging the network as well. On the account, and the last is really just on flexible security controls. So here, really you can think of it as a way to provide custom account level policies that are enforced on chain at the account level. So you could have things like multi-signature authentication, just like we have on assets. On the account, you could have a freeze function, right? So there may be a monitoring service that you subscribe to that's looking at your account. If there's any suspicious activity that's identified, maybe it can call that function to freeze your account. The other things that we get with credit cards is we have transaction limits. You might have thresholds that might require multiple signatures if you're trying to make a purchase that's, let's say, more than $1,000. And that might require 2 devices to approve, right? So you can set these transaction limits as well. And then the last one is whitelists. So American Express isn't accepted everywhere. There's a certain set of merchants that I can go use that particular card at, right? And that you can think of as a kind of whitelist, right? You can have a more tailored whitelist if you're dealing with digital assets in this format on Web3. And that'll be a way for you to actually minimize any risk. So let's say your account, your private keys were stolen, your account was compromised. There's only so much that they can transact in a given day, given your transaction limits, and they can only transact with the trusted parties that you've whitelisted, which likely means you probably have a path to get those funds back, right? So the potential for damage here is far less. The last piece I'll hint on here that I think is really critical is that there's this huge potential now for us to define open, standardized, decentralized controls that everybody can share. Right? We have it to some degree if we look at the card networks and the controls that they have, the formats, things like CBC, verification codes. Those flows are largely standardized. They're not the same, but these are opportunities for us to kind of bring this down a level in the Web3 world to the protocols. And it's a challenge today because right now, this is not at the protocol level. So these are things where we still have to go off chain and proposals are happening to now bring this on chain. If we just move to the next slide here, I just want to touch on a little bit how this is currently being implemented. So if we look at how account abstraction is being implemented, I'm not going to touch on this all, just conscious of time, but I would encourage our developer community to really look at EIP 4337. This is a relatively mature one. It doesn't require changes to the Ethereum protocol. So I think there's some viability for this to move forward and mature. And I'm very encouraged by some other EVM compatible chains that are already experimenting with this. There are 3 other proposals too that have been put out as EIPs. I have them listed here. These each do require changes to Ethereum's consensus protocol. So less likely, I think, for active development to start on those. But certainly for 4337, there's viability. So with that, I'm just going to jump to the next slide here and close out with some parting thoughts. Personally not listed, but something really to consider, I said it earlier, is that look at what's shifting, right, from the enterprise level to the ecosystem. So we know that that's how we're representing value today via tokens, how we're managing that value. That can go further when we think about self-custody. And then even more so, what else would we benefit from to move to shared infrastructure? And that's really how we're going to further evolve these rails. Right? I think there's huge opportunities if we think about how we can maybe do regulation differently, right? And where those controls should sit. Even something like tax, which is, you know, kind of a process that comes after the fact, right? Because that's something that we could enable on-chain. And does it happen at the contract level? Are there things that need to happen at the protocol level to support some of these use cases? And just wrapping up here on a few of the items that I touched on earlier, tokenization is critical to driving more value in Web3. We had heard it from Neri yesterday. They said tokenize everything. I don't know if I would go that far, but definitely most things. I think anything that can be tokenized eventually will be, as long as there's a true benefit to be realized. Secondly, here is expand your Web3 connections. This is a team sport. Build for integration and collaboration. The flexibility and the resiliency of your business really depends on it. Adopt open standards to support scaling of the ecosystem. If you're not doing that, then you're likely committing to some technical debt, and you're maybe artificially introducing friction to adoption, which is really the biggest challenge to getting success. And then you may also be isolating yourself from your broader ecosystem of support. So please adopt open standards, right? If you need a fungible token, use an ERC20, because that already gives you access to all of this great wallet technology that everybody else is building. If you're not, then you're going to have to roll your own, right? And that's not going to scale. Last but not least here, consider account abstraction to help promote really what I see as potential next wave of adoption. And this addresses significant challenges to the self-custody experience today. Like, we need to get to a place where we're not saying not your keys, not your crypto, and also where, you know, my grandmother could go and use this, right? We need to do so in a way that's openly standardized and decentralized. And with that, I think I'm wrapped. So thank you so much, everyone, for your time. I hope you found this valuable. With that, I'll turn it back over to Duncan.
Well, thanks, Alwyn. That was brilliant. Some real insights into how one should design an application for the blockchain using tokens. And I certainly agree with tokenize everything. I might add tokenize everything and then turn them into ZKP commitments, but that's just me.
Yeah, the privacy challenge is still very real, right? We need to find the right balance with those. And I think the great work of you and our R&D team is it's going to help move us in that direction.
Great stuff. Well, thank you very much. We don't have any questions for you, which means you explained it all perfectly. So we'll let you go. So thanks very much.
Thank you.
Right, coming back to our regulation theme, this is kind of about where security meets regulation and compliance. You will often find yourself in a situation where you have to look after somebody's keys. For good security, you might split those keys apart, you might shard them. And at some point, an auditor is going to come along and they're going to say, well, prove you've actually got all those key shards and you could put them together and you could give your customer their tokens back. And you might actually struggle to do that without weakening your security. But there's a way to fix that. And I have my good friend Yair here to tell us about that. Now, if you're in this business, you might have used a threshold signature. you've to thank for that, because he kind of invented threshold signatures, didn't you?
Yes.
You're on the paper.
Yes, I am.
Yeah. So I will turn it over to you,
Great, thank you so much. Well, it's a wonder, that we've been working in cryptography for so many years, and we're actually talking about wallet backups. You'd think that problem has been solved. Anyone that's watched in the news and listened and of some people having lost their keys and the potential problems that they face around loss of a wallet key, it can be very significant. We've heard of people losing hundreds of millions. We know there are lots of challenges around wallet backup. And though it seems like an easy issue, managing keys has always been a problem. Ever since I started my career, we've been talking about managing keys, managing backups, being able to solve that. And now we're in the whole crypto space, and we're still talking to various people, and they still find it a challenging effort. We're going to talk a little bit about it. We're going to talk about it from a regulatory side as well. We're going to talk about it, how others may want also to understand your backups and the reason why. The standard disclaimer, let me add a couple others. I'm going to talk about this from a very high level. I'm not necessarily going to show the best techniques. I wanted to do this as one that is educational and one can look at a basic idea and how one can work it through. The approach that will be presented is not necessarily the most elegant one. It doesn't give you all the features, but it should be one that is understandable, and I'll talk about how one can extend it beyond as well. So going back to talking about wallets, there's lots of different types of wallets out there. We talk about standard signing, meaning there's a single signature. There's multi-party computation. There's multi-signatures. Each of them have their own little properties that one can address. The single signature can be prone to single points of abuse, but they're much easier to implement. Oftentimes that when they're using a single key on such a system without sharding it, you may actually, without doing it as an MPC, you may end up sharding the keys as well as part of your backup. MPC, in many ways, is very robust. You can make like 3 out of 5 systems or different kinds of thresholds, and those have some aspects of backup inherently in them. They're also very resilient to single points of attack, and they do give some other properties which we'll talk about later. And then there's multi-signatures, which is you can have multiple keys, and even one of those keys could be an MPC approach. The multi-signatures and MPC solutions tend to be very robust against adversaries and therefore very commonly used. But across every one of these, you have one basic issue, which is you have something that's a secret, whether it's called a key or a shard, you have to back it up. If you don't back it up, especially inside a digital asset type wallet, then you will not have access to your funds. And there's no 800 number to call back or anything else like that to be able to derive that key. So regardless of the way you're approaching it, you will have to consider backups. So let's talk a little bit about a problem statement. One of the things that you want to do when you're doing a backup, and let's think about it in the context of MPC, this doesn't apply necessarily only to MPC. If you were to take a multi-signature or even a single signature solution, and you were to split the keys into shards, not necessarily using it as an MPC, this would also be applicable. And there are actually other variations. But the first thing you want to do is, if you have all these shards in different places, you want to be able to validate for yourself that those shards are going to work at a time that you need them. But you may also want to be able to prove to others the ability to do that. And that can be a lot of different groups of people. One, it could be your own auditor. So EY does auditing. we do test people's backups, or we do ensure that they do test their backups as part of various audits. Your customer may want to know it, and they may want to know that their key, their specific key, is backed up, as opposed to you telling them, we do backup keys. And regulators are oftentimes, that's generally a requirement, especially for regulated institutions, to be able to demonstrate that they've done regular backups. And there could be possibilities that insure, let's say you're insured against, that you have proper protection against a backup, and your insurer will want to validate that you do this on a regular basis. But each and every one of those cases where you're having a third party validate, you don't want to give them any information. You just want to demonstrate to them that you can do the backup. The other thing that you would want to do on a backup is you want to be able to deal with organizational changes. An example is someone leaving your organization. What happens if they leave? They did a backup process with you. They know some secrets because they actually held it at some point in time. They may hold a password or a key or something else, and they leave, and what's been seen has been seen, and you want to be able to deal with how to manage it so if several of your employees leave, that you've not really lost any information in that process. So these are kind of real world scenarios that we talk about with our clients and others in the industry. Our approach will be basically two things. One is we want to encrypt shards. And we want to encrypt the shards in a manner that we can validate that the encryption of these shards are going to be each encrypted separately, that the encryption of the shards, when they're brought together, will be able to regenerate the key. We have various variations around it, but the point is that we want to make sure that each of those encryptions, whether they stay separate as encryption, and there's a way we can combine them as well, that what's encrypted is actually going to be able to regenerate the wallet key. The second thing is, well, if we've encrypted them, we'll want to be able to demonstrate that we can actually decrypt them. So we'll go through today, and we're going to talk about how one can do this. I'm going to use a useful form, a very common form, a very old approach of doing it. It makes it very easy for us to do zero-knowledge proofs. So therefore, that's one of the reasons I wanted to describe it. We'll talk about zero-knowledge proof of statements around how this is achieved. We'll talk about extending this. One of the aspects is, for instance, if you're proving to someone that you're backing up a key, one of the things you may want to do is during that proof, demonstrate the point in time or a range of point in time for which that proof was done. So what you wouldn't want, or at least someone that's verifying if you're a third party, what you wouldn't want is the company that is giving you the proof, hey, they created 10 proofs at the time that they generated a key, and every year they give you a new one. So you wouldn't want to have that happen. You wouldn't want to have it in a manner that could be, in a sense, time-stamped. We'll talk a little bit about HD wallets, which will use a slightly different techniques, but again, give some flavor around some of the techniques that are used in the industry, and we'll talk about robustness and various ways to encrypt wallets and encrypt shards. So the encryption we're going to use is one-time pad. Many of you are familiar with it. I know there are several people starting out who this is a new area, and it's not a very difficult one. Basically, what we're doing is you think about it as a circle, kind of like a clock, and you're doing addition kind of in a clock. It's going to be a larger clock. It's going to be a very large prime, more than likely. But basically, you choose a key, you choose a message, and you add them. And you do it as you would do it in a clock-type fashion. So if you think about something being, let's say, 11 o'clock plus 2 hours more, that would be 1 o'clock because it's 1,300 hours, right? And the niceness about this approach is it's very easy to go back and forth, right? So you just perform the operation backwards. If you have the message or you have the output of it, the ciphertext, you can certainly go backwards by just subtracting the key. The nice aspects of it is that it does make, when we approach this matter, we use a random key. And therefore, every ciphertext that we generate looks random. And in fact, that's one of the benefits of it. It is random. And we're going to use that in our zero knowledge proof because it's very easy to simulate randomness. And the concept of zero knowledge is about simulations. Many of you may think about this being, as a one-time pad, being secure against the infinitely powerful computer. In our case, even though the one-time pad is by itself meet that level of security, because we are providing a public key, we will actually only have a security of our total system no more than the discrete log, which is the security of the wallet itself. So let's talk a little bit about secret sharing. In a secret sharing scheme, there's many types of access structure. Oftentimes we'll talk about threshold schemes, but we don't actually always have to do a threshold scheme. It doesn't have to be like a 3 out of 5 or any threshold is a certain number. Oftentimes we'll do things that are different kinds of access structures. So for instance, we may want to have an access structure where there's one group A, a separate group B, and a third group C, and one requires one from each of those groups. Why would we do that? Well, we may want to have like group A sitting on AWS, group B sitting on Azure, group C being on-prem, or being yet in GCP or a different infrastructure, right? We may want to have some of the groups running Windows, some of the group running Unix, some of the groups running something else, right? We may have different teams. And for an adversary to break into that, they would need to break into all those different components. So if Group A had Windows and Group B had Unix, you would be forced to break into both Windows and Unix. If Windows had a vulnerability or Unix had a vulnerability that you were using, then you would still not be exposed. We're going to look at, again, a very simplistic secret sharing. It's actually a common one that's used, where we look at all the possibilities, and every row will make it so that the sums of those rows just add up to the secret. We'll generate them in a very random way, and when we add them in a random way, they all add up to the secret. And this happens to be a secure type system. Now, there are other ways of doing this. Many of you may have heard of things like Lagrange interpolation and such. And the approach we take actually does work for Lagrange interpolation, but this makes our life easy because we talked about one-time pad. Remember, one-time pad, all it did was just add the key with the secret, with the message. We're just doing, again, an approach that does a bunch of additions. I want to talk a little bit about zero-knowledge proofs and how this relates to what we want to do, right? When we're doing a zero-knowledge proof, one of the things that we want to ensure is that when we have the proof, that the proof is, we can demonstrate when it's correct that it is actually correct. So in our case, for a backup system, if I'm checking my backup and I get these proofs, I want to be pretty sure that those are. And if something is wrong, I want to be able to identify if that proof is wrong. I definitely want it to be distinctly correct that it is false, if the proof is false. The last part is a zero knowledge, which is the way we demonstrate that something is not breakable is that we actually create a simulation, and we take a simulation and we take a real view of the interactions. And what we do is, against the two, we look to see if we can distinguish between the two. If you can't distinguish between the two, then it's not possible to determine between the fake one, which you generated on your own, it didn't even know the secret, and a real one. And this is what we're going to use in our approach. The reason we're going to use a one-time pad as an example is that you can always simulate a random number. So what were we going to do? again, our approach is going to be the one that is a simplistic one for our example today. We'll take a key and we'll split it up into 3 ways. And we can use that previous example that we may make multiple breakups of that key, just as we did with that access structure that was previously shown. Each of those will be encrypted with a random number. So the key, or the shard in our case, is going to be K1, K2, K3 for one of the rows. The R1, R2, and R3 are going to be encryption against each of those. And then we're going to create separate encryptions. And we're going to publish those. Now, we could actually do some other things to even make this even a little bit more secure, but for our conversation today, we're just going to publish those. And we're going to publish a witness of the key. Again, there's other approaches to doing this. But what this gives us the ability is we now can see that if we take each of those encryptions, E1, E2, and E3, and we add them up, then we're going to get the K1 plus K2 plus K3, which is the key, and the R1 plus R2 plus R3, which is the key for the wallet, and the R1 plus R2 plus R3, which is the key that is the set of keys that are used to encrypt each of the shards. And we now can generate a proof of the decryption keys. So we can go in and we can demonstrate each of the decryption keys. What we're going to do is we can take that E1 plus E plus E2 and E3, and we can use that as a mechanism to prove that, one, here I know the secrets to decrypt those, as well as that because the combination generates a key, that I'm actually able to demonstrate the actual key that is being produced. So let me talk a little bit about proactive security here. What we're generating is encryptions of keys, and when they add them up together, the encryptions, it becomes an encryption of the wallet key, and we have a bunch of shards that are also now being used to encrypt the wallet key. What we can do with a proactive security, and this is a common mechanism that we can do with a wallet, is that each of those keys can now be, each of the keys that are the decryption key can now be regenerated in such a manner for which we can reshard them. So we can start with a set of shards, the squares, which is on the left, and those shards generate each of the R1s, R2, and R3s, and the circles generate a set of secondary shards. We are able to permute or configure the square shards into circle shards in such a way that the circle shards don't teach you anything about the previous one. So if one of the square shards happens to be compromised, we are able to restructure our decryption keys for our wallet keys. The beauty of that is we can constantly change the encryptions that we created. By constantly changing the encryptions, we can then be able to ensure that even our backup keys, should they get compromised, which is an unlikely thing because they're not active, they are not going to be, that we can actually regenerate new shards for those. We can also do another thing. We can also change the number of shareholders. We can change the access structure. We can actually add new shard holders. We can even remove shard holders. So if an employee leaves the organization, then we are able to recreate new shards. If an employee moves to a different team, we can recreate new shards. And these are the shards of the decryption key as opposed to the shards of the wallet key. So I want to talk about a little bit what the next step one can do. So what we've done is we've taken a wallet key. It's been sharded. We took each of those shards and we encrypted them with a separate set of keys. We took those keys, and we now can get to the actual wallet key. And on an HD wallet, that's the leftmost thing on this tree diagram. But you may want to do something else. You may want to be able to prove it all the way upwards through the wallet. And you may want to do it at an account level. So for instance, let's say someone had an account, they know their expert because they're having a watch wallet, and they want to be able to say, prove to me that you can actually back up that you actually have the backups for my watch wallet at that account number. Well, each of those arrows really represents a hash, and it's sort of a combination of a hash. And what we can do here is we can take the index, which is a number that's going to be thrown into the calculation. It's a number that can be known. It's nothing that is secret. There's a piece of chain code. This is a random number, which we generally do not provide externally. And the public key. What we can do is we can take these and we can then hash each of those individually. And we can then go through and do some ZK snarks, which will perform each of those arrow functions, which takes a composition of those three elements, the index, the chain code, the public key, and be able to generate a new set of indexes, chain code, and public key for the next layer within the HD wallet. That in itself will generate the next layer within the HD wallet, and we can continue to follow through each of those. We'll do this now with ZK Snark because we're using hash functions. So what this gives us is the ability to now start with an HD wallet and then being able to prove out across the HD wallet to a specific account if that is what is necessary. So what have we accomplished? One is we wanted to be able to validate the wallet that we are generating, that we validated that we have done a backup. The way we've done it is we split up the shards into individual encryptions, and we've encrypted each of those shards separately. And by doing that, we were able to verify that that particular shard, that those encryptions will generate the original wallet key, and that we can actually verify that the shards actually decrypt, that we can actually decrypt each of those encryptions. We can use the same mechanism now to prove that to outside parties because these are encryptions and they're zero knowledge proofs, and those can be provided to third parties. We can also manage things around making changes. We talked about how to make something proactive. We can change those encryptions of the shards, and therefore we are always able to add, delete, change users, and be able to perform this. And again, what we can do this is we can do this all the way from having the shards of the wallet key as an HD wallet, moving it on down, publishing the proofs, verifying the root of the HD wallet, and then we can use, for instance, ZK snarks, walking down the HD wallet and being able to verify exactly at the point of an account or whatever level. We can do this without actually having to create transactions. So now we are able to perform a proof around our wallet and verifying that we have a backup, and we don't actually have to create transactions, which we oftentimes are not able to do that. The very fact that we have a zero knowledge proof gives us all the capabilities that we actually need to be able to approach that. So some final thoughts around what we can do. So the basic approach has been encrypting shards, proving those encryptions are correct with zero knowledge proofs. One of the things we can do is during that encryption, we can actually take data, for instance, let's say a block on the blockchain, and incorporate that into the zero knowledge proof. What that guarantees is that that piece of information is incorporated in the zero knowledge proof, ensures that that zero knowledge proof could only have been performed after that block. This now guarantees us the ability to this guarantees us that that proof was done only after a certain point in time. It turns out that even when we are auditors and some other things, as well as sending out to third parties, you may not want to provide your public key out. We've also have a mechanism which one can obfuscate that public key. We can also obfuscate the encryption, so makes it so that really no information is actually leaked out for this whole process. And lastly, we talked a little bit about robustness. That robustness was generated around bringing keys together. That when we bring those keys together, we are able to decrypt, but we can add robustness in the sense that we can add players and remove players. But the solution also has an interesting property that we can have separate encryption of keys, or we can bring them in together and we actually have a single encryption of the wallet key and multiple shards that are able to protect it. That gives us the ability to actually change the shard system of the MPC on the backup solution and still have shards that will work up in a production environment. Let me just add a couple final points. I only talked about wallet key management and protecting of wallet keys. And, disaster recovery is a much more complex aspect. Wallet keys and bringing up the wallet keys is an interesting aspect, but it is only a portion of what one requires for disaster recovery. You need to be able to potentially create, once you get those wallet keys, your systems may not be available. You may need to do things, for instance, such as being able to generate raw transactions, sign transactions. So a complete solution around a disaster recovery needs to be considered in a broader sense. We only touch one of the smaller aspects, which is a part of just managing keys. Thank you.
Well, thanks very much. Yeah,
Yes.
that was amazing. It's really good to see ZKP being used not just on the blockchain, but actually to facilitate audit as well.
Yeah.
So, marvellous. Thank you very much.
Thank you.
Okay, so ladies and gentlemen, we're on to our last talk of the day. And I'm going to introduce Monica, Mark and Pierre. They are partners from our financial services and law businesses. So I'm seriously outranked here. But you've heard a lot this afternoon about regulatory compliance and you may be wondering, well, how can I find out a bit more about that? They're here to tell you.
Thank you very much. So good afternoon, everybody. We are the last session, not of the day, but of the week. So it's really a pleasure to be here. Hopefully you will stay with us for the next 15 minutes. So what I'm going to do, I'm going to present the platform, and then Monica and Mark will introduce themselves and explain what they do with regard to this platform. A bit of slide. We are consultants, so we like slide. So what is this platform? This platform is first and foremost about content. It's about content with regard to digital assets, primarily focused on financial services, but it can be used elsewhere, as we are going to explain. So content, what is a content? Well, as you know, there is a certain way to describe a digital asset, so you need a taxonomy. There is a certain way to understand the legal and regulatory impact of using digital assets, so we have a lot of legal and regulatory content. There's also risk and control related to digital assets. And then more from a business perspective, you need to understand what are the changes required to implement digital asset business activities and the amount of capital you need to put aside. So first and foremost, this platform is about content. But of course, content itself is not very useful. That's why we have attached a lot of functionality around content. It's pretty straightforward. You can see that on the slide. I think I will highlight one thing. It's a huge amount of content. So we put a lot of emphasis on visualization, on a simple way to access a vast amount of content very quickly. Number three, it's not only about content, it's also about services. We are a service company, and on top of that content, the platform, we have consultants, we have people that provide services attached to this platform. Services, we refresh the content on a quarterly basis, we upgrade the functionality. More importantly, we are accessible to the people that use this platform, and we can do deep dive, we can advise, we can, what a typical consultant will do. So there is a service component that is very important. Now, what are the users? The users are, as I said, are financial services firms, but also tech firms that are involved in digital activities. So it's a wide range of users and companies. And within these firms, it's, different people will use it. So obviously the business, the front office, but the tech people, the reg people, the finance people, the legal people, they all need to understand what digital asset activity means from a risk, from a legal, from a regulatory perspective. But what we see talking to our client is not only them that are interested with the platform, is their client, because their clients are also keen to know what's going on. So that's the platform, that's the EY Digital Asset Insight and Assessment Platform. Now, because it's so much content-driven, I would like to introduce you now first Mark Selvarajan. He is a leader of our business and risk and control platform. He's going to introduce himself, and he's going to give a bit of some idea about what the content is all about.
Great, thank you very much, Pierre. Thank you all for joining. So I'm Mark Selvarajan, as Pierre mentioned. I'm a partner in our risk practice, and I look after a lot of our digital assets consulting here in the UK and working with our broader global teams. So you've heard a lot about content. So let's zero in on exactly what we mean. Now, when we first developed this platform, it was in response to a relatively simple question from our traditional finance banking clients and our crypto or fintech native clients that were involved in digital assets. And that question was, as we grow our business, are we able to do so based on legal and regulatory constraints? And how do we do so in a way that's sustainable, given all of the nuances of risks and controls that we need to implement? So we set about developing key elements of content to help them answer that question. So that would mean we defined detailed activities for tokenization, trading stablecoins, trading crypto, being involved in CBDCs as they develop their proof of concepts. We looked at those activities, catalogued them in quite a detailed way. We also then looked at, for every activity, what risks should you be worried about? Financial risks, non-financial risks. And we went down to quite a granular level of detail. And then we looked at what are the controls that you need to mitigate those risks, and then overlaid all of that with what are the regulatory and legal constraints in a given country that you might be doing business in. So we did that within EY, but then we worked with our clients, with those crypto and fintech natives, with those banks to update and enhance that content, put it into the platform. As Pierre already mentioned, it's not static. We're constantly working on this and expanding the use cases. So we started with trading and custody. We're moving into tokenization. We're looking at more and more specific use cases and really just responding to the demands of our clients as they make requests of us. So I've touched on the risk and control side, but a big part of this is the legal and reg, particularly as it goes country by country. So I'll pass over to Monica to tell us a little bit about the legal aspect.
Thanks, Mark. Hi, I'm Monica Gogner. I'm the lawyer in the group, I guess. I head the financial regulation team in EY Law and delighted to be here. It's actually been a very exciting project to work on and a fantastic tool to build in collaboration with our consulting colleagues, particularly actually for exactly what Mark has said. If you look at any of the regulatory or legal restrictions that are involved in terms of the key questions of how do you look at crypto, is it permissible to do certain activities within a jurisdiction or not? Actually, just giving a pure legal answer is never enough. You actually need to wrap it up with your risk, your operations, your systems and controls. And so actually working collaboratively together, we've managed to create a tool and information in a user-friendly format that actually does present this tool very, very powerfully. How do we do it? Well, as I said, I lead the legal team within the financial regulation sphere in the UK, but we work very, very closely with all of our EY Law colleagues across Europe and actually across the world. And that helps us ensure that we are making sure that we're up to date with all the key regulations that come in, and also, frankly, some of the gossip that comes in relation to, well, what is going on in terms of the progression of this law in this jurisdiction? and what most crucially will be the cross-border impact of that regulation if, for example, like most global financial services firms, you don't operate in one jurisdiction. So I think that's really a strength that we do have in terms of the tool that we've created.
Yeah, thanks, Monica. What is important, and again, behind Monica and Mark, there's armies of people that help them to create this content and, as Mark mentioned, refresh it, upgrade it, and so on and so forth. So that's one point. It represents the entirety of EY. It's a global, I think you mentioned that, Monica. It's not because we are based in the UK that is only UK focused. As we are going to see through a very quick demo, it includes everything. It's a global tool with different view on different countries. Look, my problem is I have different glasses to look shortly, so it's not ideal. But look, this is one view. I said we are going to focus on visualization. Hopefully, we are going to be able to demonstrate to you. So this is, in effect, I will go to the top, the jurisdiction view. And you can see in the middle, this is a version as of January 2023. This is because there is different version, and as we said, we upgrade on a quarterly basis. So that you have an index 80%, and this 80% in that particular view tell you how the market, from a risk control, legal and reg perspective, is ready to embrace the crypto and digital asset activity. And by that I mean, for example, if I look at Monica, I will ask her, if we go to France, Monica, can we, is it permissible, is it permissible to engage in trading activities? And Monica will, because she's a lawyer, will look at the law, first of all, at the regulation and the law, and she will give me an answer. And she will say, yes, it's permissible, or no, it's not permissible. In the same time, I will look at Mark and say, Mark, okay, it's permissible from a legal perspective, but do you think for this specific activity, trading, spot trading activity, do you think from a risk and control perspective, are we safe to trade in France this type of instrument? And Mark would say, look, let me review and I will give you an answer. So that's what basically we try to represent. Now, you see 80%, that globally doesn't mean much. Then I will look to Switzerland, the index is 83%. If I go to trading, so you will see, not a lot of clicks here, and very quickly, sorry, there's a little, I will go to trading, double click, and then suddenly I can drill down from trading to the different trading activities, spot, vanilla, product, forward product, and so on and so forth. Now,
I do think that's very important, because when you look at how you utilise regulation and laws for permissibility, not every product will have the same answer. So what we've tried to do in the tool is to show and highlight those differences. So to Mark's point, as we move to look at tokenization, again, the regulatory and legal regime there will be different compared to the operational regime. So actually, this tool helps you differentiate between those different products.
Products and, Monica, and type of cryptocurrency in this case. So if I click on Paxos here, you'll see all the data I've got, and I will go to you because, you know, you're nicer than Mark, so I will stay with the legal assessment. You can see for Paxos is permissible, and when I click on permissible, I've got the explanation. And that's what Monica and her team have worked on for weeks and possibly months to provide a legal view on that asset. Now, because Mark is also a friend, I will go to challenges, and there is a risk and the control view here.
Yeah, so absolutely. So for trading Paxos in France, I suppose the jurisdiction doesn't matter so much, but for trading Paxos in a given jurisdiction, we looked at all of the different risk types, and then we ranked them to say, okay, well, what's the scale of that risk? Is it significantly different from trading a regular financial product? So that variation by activity, by jurisdiction, by underlying digital asset, whether it's crypto, stablecoin, CBDC, whatever it may be, is all sitting there in the tool, and you can keep drilling down as needed.
So what we just demonstrated is in 3 clicks, you can go from the top to the bottom data, well, the most granular piece of information and very useful information. We won't have time We won't have time to do a comprehensive demo. So I just want to leave you with this kind of, that's the kind of homepage. We just show you what the digital asset index can do. There are other functionalities. So there is a digital asset share. That's where the users of the tool can share their views, their comments, and we have developed a lot of benchmarks based on that. There is a news, interesting feature. So we capture all the news that we can see, and we map the news to the topic we've just managed, we just discussed, so legal risk. So suddenly you have a very rich view of the world. Last but not least, well, there's two things. Digital asset learning. This is where we put a lot of podcasts, document where you can get access to education on these different topics. Information is interesting, but when you have podcasts, is even better. Last but not least, and this is what we are currently developing, it's not in place yet, is you can use this tool to assess yourself. It's not only an EY view of the world, it's when the banks or the companies can assess themselves with regard to their digital activities. And I think that's all for us.
Well, thank you very much, everybody. We don't actually have any questions for you, which I take to mean you explained it perfectly.
Very good.
So, yeah.
Very much.
Great.
Thank you very much.
Okay.
Thank you.
Well, ladies and gentlemen, that was the last talk of the day, and actually the last talk of the summit. So, if you haven't already, there's still time to claim your NFT. The barcode should be coming up at some point soon. But other than that, I'll say thank you for your attention, and we'll see you all next year.